Okay. Okay. Good morning, everybody. Welcome back. I hope you had a wonderful dinner last night. I actually enjoyed it, and good, interesting conversations. We are on the second day today. It's morning. We will have 3 spectacular talks. I hope so, at least. No pressure. The first one is actually also someone I'm super excited that she accepted. It's Gita Kutunyok. She has the Bavarian Chair for Mathematical Foundations of AI at LMU, or Ludwig Maximilians University, and is also affiliated with the DLR, German Aerospace Center, and the University of Tromsø. She got a diploma in mathematics and computer science, as well as her PhD degree from the University of Paderborn, and a habilitation in mathematics from the University of Gießen. He has many awards, including the Research Prize of the Gießen University and the Heisenberg Fellowship and the Caven Prize by the DFG. He's currently director of the Konrad Zuse School of Excellence in Reliable AI in Munich. She's initiator and spokesperson of the DFG Priority Program, Theoretical Foundations of Deep Learning, and of the really fantastic AI Hub at LMU. Her work covers applied and computational harmonic analysis, artificial intelligence, compressed sensing, deep learning, imaging sciences, inverse problems, and applications to life sciences, robotics. She actually bought a robot recently, and telecommunication. With that, I do not want to steal too much of her time. Gita, the stage is yours. Thank you.
Yeah, thanks a lot, Wolfram, for the very nice introduction. Also, thanks so much for the invitation. It's great to be here. I have to apologize that I could not be here yesterday, but I was invited for a keynote talk in Hamburg and just arrived last night. So unfortunately, I also missed the spectacular dinner, but I'm glad to be here now. I would like to speak a bit about, I think, from my viewpoint, two major problems these days in AI, and so also in particular embodied AI, which is reliability and also sustainability. I would like to show you a bit the approach from a more foundational, theoretical side, and you will see that in a very natural way. This will lead us also to, let's say, the vision of next generation AI computing. Yeah, so I think I don't need to tell anyone, how important AI is these days. We are expecting during the next 5 years a complete change of our society in its full breadth, and certainly embodied AI plays one major role in this respect. But as said, I think there are 2 main problems, besides others, which we need to tackle, and one of that is reliability. So let me remind you that we still have a lot of problems with reliability. So we have problems with safety. We know about, for instance, accidents with self-driving cars. We have problems with security. One can hack into those systems, taking over control, modifying things slightly so that a human would not recognize the difference. We have problems with privacy. So in particular in Germany, we have very strong privacy rules. And in many areas, like for instance in the health sector, data is scarce. So privacy violations and acquiring large data sets is a major problem. And then I might say problems with responsibility. Many of these decisions, we cannot really understand how they are taken, so that affects also the trustworthiness, the acceptance, for instance, in society. And as said, many of these are black box decisions and biased decisions. So this is one main problem, and what turned out also over time is that a foundational perspective is extremely important for all those aspects, in particular, for instance, for safety. So here we are in Germany, and we have from telecommunication, the Federal Telecommunication Agency, the Bundesnetzagentur, and for critical infrastructure, they don't use AI these days because all these, let's say, theoretical guarantees are at present still missing. So this is one key problem. Another problem is sustainability. And so here, in particular in the US and other countries, we see these hyperscale data centers for training AI systems. As you might know, in Germany, it is not possible to immediately build nuclear power plants next to the next data center. So sustainability is a problem, but I think it's even more severe than that. And so what I show here is a graph from the Semiconductor Research Corporation for the Biden administration. So what you see here, so let's see how that works. Okay, yeah. Yeah, so you see here the world energy production over time. And I will show you the energy we just need for communication. Also communication between AI agents over time, and this is how it looks. And so you see the problem here. I mean, if we continue that way, I mean, the way we do, we will reach the world energy production eventually. If we are a little bit smarter and use, instead of CPUs, GPUs, we can lower this curve, but still, this is a serious problem. And if we are even more smarter, we use so we use new platforms. So we also change the hardware. We can do even better. And then if we, in addition, also change the software, we can lower this curve. Sorry, this is actually very sensitive. We can lower this curve even further. And so here you see, for instance, I mean, we will also hear a talk by Frank in a moment. So this new method here for communication, this is by Holger Bocher and Frank Fitzek. So I think the main message here is not changing only the software, but changing the software together with the hardware, and particularly also in embodied AI. I think this is also one key message, that both go hand in hand. Yeah? So even for, let's say, cognitive AI, this is essential. So these are the two main problems I would like to discuss here and tackle. But let me just ask, I mean, because Redezeit is 0, so do you have... okay, because here because it didn't turn on, so it's okay. Okay, good. So, I mean, let's take a mathematical perspective. And the main point, I think most of you know that, what I would like to make here is that AI is based on mathematics. Yeah? So we have very concrete formulas where we can also then analyze stability, we can analyze privacy aspects, we can analyze black box aspects. So in that sense, I mean, from my perspective, from a theoretical perspective, that's a very nice situation. So we are on solid ground here. And if we look at the workflow of how to apply, for instance, deep neural networks just as a starting point, this will show what we require for ensuring reliability. And so this will then hold both for cognitive AI as well as also for embodied AI. Yeah? Just to remind you, I mean, we have our data, we train our neural network, we need to decide which architecture to choose. We then, once we have our trained neural network, we then do a performance check. So these are the directions, and so now for reliability, what is key is, first of all, how to set up, for instance, the architecture, how to set up also the whole environment to get the best performance. Yeah, so that's the area of expressivity. It is very well established from a theoretical point these days, but there are still a lot of things to do, in particular also then, I mean, in accordance, for instance, with hardware aspects. The training aspect, the learning aspect is one second key problem for reliability. And also here, there are many theoretical results at present, what the network, let's say, learns about success guarantees, what is the best training algorithm in certain settings, but also here there's a lot of room for improvement. The third is generalization, and I think this is one main aspect for reliability. So as said, what we need are these performance guarantees. And from my viewpoint, I mean, only there this can be achieved if we have, let's say, a strong theoretical foundation. And so maybe yesterday you already heard some talks in this direction. So, and in my group, we also work on generalization aspects, but this is not what I'd like to talk about here today. I would like to focus first more now on this area of explainability, because I think in particular, I mean, there are some results already for cognitive AI, but what I feel is that in the area of embodied AI, there are many open problems in the area of explainability. But on the other hand, since we have now strong laws, like for instance the EU AI Act, AI technology, in particular also embodied AI, has to come with also explainability approaches. And so I would like to first discuss a bit my viewpoint on explainability. I would then like to turn towards the problem, can we make, let's say, in general AI, embodied AI in particular, reliable by design? So this will bring us in this world of how to learn physical laws. I will show you some results we also have with the DLR there concerning robots. And in the last part of my talk, I would like to then come to the area of sustainability, because in particular, also if you think of, for instance, underwater robots, I mean, battery and energy is a serious problem. So what I would like to discuss there is, I mean, what are chances to make things more energy efficient? And this will bring us to this area of next generation AI computing. Okay, so let's start a bit with explainability. Just to set the stage, I'm sure everybody has seen that. Everybody has seen that, yeah, so this is classical explainability, what you see here. I mean, you have here this, let's say you have here an image, a 3, the network says this is a 3, and then the explainability approach produces these heat maps indicating at each point how much the network looked at that for a certain decision. Yeah, and so on the right-hand side, you see by my dear colleague Klaus Robert Müller from the Technical University of Berlin, a very interesting example where you see that the training data was actually biased, so the network has not learned what a horse is, but only this copyright tag. So the key message here is explainability helps you also to understand whether the training process did something reasonable. So it helps to check reliability in that sense, and also, as said, I mean, understanding what are the key principles which were learned by the robot. Yeah, and so I think, I mean, from my viewpoint, I talked with a lot of, let's say, colleagues also in robotics, and explainability could be also something to, let's say, now if you use, for instance, also foundation models for robotics, if you use large training models to ensure reliability, to check a bit what has been learned, whether something reasonable has been learned. And again, I mean, the EU AI Act, I think, is something which anyhow demands this direction. Let me also say that, I mean, we have now a large-scale project in Bavaria together with the Bavarian State Ministry for Digitalization, where also the UTN and Wolfram Burgert is involved, where we aim to look at the laws, the EU AI Act within this Bavarian AI Act accelerator, and aim to make it, let's say, more accessible and ensure how this can be realized for different areas. So, for instance, Wolfram Burgert is responsible for robotics. Okay, so let me now talk a little bit about explainability. As said, I mean, from a more, let's say, high-level viewpoint, show you a bit what we have done. I apologize that this is not, I mean, yet for robotics, but I strongly believe that many of these principles can be transferred. And so I hope that then, I mean, in the future, we also have a project together, I mean, called Genius Robot with Wolfram Burgert and Björn Ommer, that some of these ideas can be also realized there. And so can also help robotics in that sense. But I think, I mean, what I find also fascinating is what does explainability then mean? Because here it's quite clear. We have our data. We know, I mean, what we would like to know. For instance, for an image, we would like to know which pixels are most important for a decision. But for robotics, it's not really clear what explainability there is. Yeah, so a robot does a certain, let's say, action. What would be an explanation? So which data does it base its decision on? Which aspects of the environment, for instance? So I think this is, let's say, an additional serious level of difficulty which comes into play there. But let me first show you what we did here. So the ultimate goal would be to communicate with an AI as a human for a reason, for a decision. And so you can then extend it also to embodied AI so that you can communicate with a robot like with a human for a reason, for a decision. From my perspective, if you would like to use explainability as, well, trustworthiness, as something to make things more reliable, what we need is that also the explainability approach itself is reliable. And so this, from my perspective, can only be done if the explainability approach is based on a rigorous mathematical foundation. And as said, I would like to show you now one of our approaches, which is based on information theory, in particular on rate distortion theory from telecommunication. So rate distortion theory, information theory, I'm sure most of you know about that. So you have two persons, you have a message, and the message is transmitted, not the whole message, but part of the message. And then Bob receives the message, he decoded it, and so this is this rate distortion trade-off, how much you send and how much the error is in the end. So now you can, this explainability framework, you can set it into place concerning information theory. So what you see here is, so you have here your neural network. You have here the original image. Then part of the image is transferred. So these are a couple of pixels maybe. Then Bob also has the neural network. He obfuscates it to bring it back to the image size, puts this in a neural network, and will make an error. So we have the rate, how much is transmitted, hopefully the relevant part of the message of the image, and you have the error which is made. So that's exactly this rate distortion framework from information theory, so you can also use a lot of theory from that perspective. So that would be the distortion, and this is what you aim for. Here we aim for a concise explanation, so we optimize over the number of pixels in this case, under the constraint that the distortion, the error, is still kept under control. So this fits perfectly in this information theoretic framework. So now we all know this is nothing you can compute. So you can do fancy mathematics in this. You can show this is NP-PP complete, and so on. And so then in this situation, what you certainly do is relax. So this is now the optimization problem we solve. This is the optimization problem which our explainability approach is based upon. You see here the balancing between the distortion and the sparsity of your explanation. So instead of counting the number of pixels which are important, you replace this by the little L1 norm of the relevance scores in each pixel. Okay, so here this is now accessible to all of mathematics. It's an explainability approach which is reliable to a certain extent. And so here you see a couple of images. Again, I mean, this is always nice to show these imaging situations. And what you see here is you have a network which says this is a dog. You see here explanations, and this is a very sparse explanation. So ours is tuned for sparsity, and this is what you see and observe here. So this is then a comparison with other approaches, and what you observe here is that our approach is the best in this regime, where you aim for very sparse explanations and also would like to have a very small error. And so you will say, well, ours is tuned for that in any case, but then, I mean, the other approaches use this measure also for comparison. You can extend this in different ways. It's a very flexible approach, and therefore I say it's a very feasible that this can be also extended to problems, in particular in this area of embodied AI. So here we extended it in two ways. I mean, first of all, I mean, this obfuscation with random pixels is very strange, so you can use in painting guns to do this. And also the other way we extended this was to look at not just pixel-based explanations, but combinations of pixels. And so combinations of pixels, you know, there are approaches like superpixels, and so on. So here, what you see is we have here a decomposition of the data in terms of wavelets. So computer vision, this is one way to do that. So if you would now like to have, for instance, an embodied AI system, so images are one aspect in addition to a lot of other data. And so, for instance, here you could look at combinations in this way, which seems to be very natural. And so here you see an explanation again from telecommunication, how we apply our approach, what you observe here. So this is joint work with Giuseppe Caira, also from TU Berlin actually. So you see here a city map. You see the red dots are cell phone users, the white blob is a cell tower, and you see here the radio map computed by a double unit, indeed without even any training data. So we have some papers in that direction as well. But what you see here is the network seems to have made a mistake. So you see here this black area of bad reception, although if you stand here, you stand right in front of the cell tower. And so then you ask with these explainability approaches, what did the network look at to reach that conclusion? And you see here on the right-hand side the explanation for that. And indeed, these cell phone users have bad reception, so it makes sense to put here an area of bad reception. And what turned out in the end was there was actually a building missing in this city map. So the data was faulty, the network did something correct. And all of this you can find out by explainability approaches. And maybe as a last example, before I show you one also theoretical result to show you that, I mean, this rigorous mathematical foundation has a huge value. So here, I mean, you have two different images which were misclassified. As you see here, I mean, this being a diaper and this being a screw, and so you can now overlay that with explanation to see what the network has seen to reach a wrong conclusion. And so here, you see this looks a bit like a baby, so diaper is not far off, and this looks a bit like a screw. And so then you can counteract. So in that sense, I mean, explainability, I think, is extremely valuable, and so I'm looking forward also in the project with Wolfram to bring these ideas a bit more also to robotics. Let me say as a last part concerning explainability, you can also do, let's say, rigorous theory in this direction. So what we observed here was that sometimes explanations are not faithful. So you see here, for instance, an image, a cloak, you see here the edges, and you see here different explanations, and for instance, this explanation is not faithful in the sense that it invents new edges. Yeah, so this is a strange explanation, it's not consistent with the original image, and by this strong mathematical foundation, you can then show rigorously what you see here, that, maybe I should do it this way, yeah, so that you, so that the edge structure, which fancy terms in mathematics, the way Franz said, so the edge structure of the explanation is a subset of the edge structure of the original image if you use our method, so if you use this cartoon method. Yeah, so that's what I mean with, I mean, if you have a theoretical foundation like information theory, then you can ensure that your explainability and your explanations you can actually trust. Yeah, because otherwise, I mean, it produces fancy pictures, but it doesn't mean anything. Okay, so explainability, I mean, you can find out whether mistakes have been made, you can find out what neural networks, how they act, how AI basically reaches decisions. But then, I mean, a lot of mistakes are made. Yeah, and so you can find out why, but it doesn't help you much to ensure that this doesn't happen again. This goes a bit further, I mean, in reliability by design. Yeah? So physics-informed neural networks, I'm sure most of you also have heard of that. This raises the question how you can actually ensure that physics is obeyed. And so this brings me to the direction of, can we actually learn physical laws and then incorporate that in the design of the system? You can also view it a different way, yeah? So you train your model, for instance, the foundation model, you want to understand whether it learned something reasonable, and so you might want to know whether, for instance, physical laws were learned. So this is all a question of, you have given data, can you actually understand the underlying laws? For instance, to improve your modeling, or to check also whether, let's say, physical laws have been correctly obeyed. And so this has been done in former times. We are not there anymore. There are some approaches for this learning physical laws, AI discard towards an AI physicist, and so on. So the key question is what you see here. You have your data. So this could be, for instance, I mean, what the robot learned. It could be just other types of data where you would like to deduce physical laws. Maybe to understand what has been learned, maybe also to help and aid making it more reliable. Let me first spend one slide on the theory, and then I will show you some results which you derive with the DLR. So what we observed is that there is actually barely any theory in this direction. Yeah? So I mean, there are many algorithms, they are often very unstable, and one reason is also that, for instance, you see here, we have here two partial differential equations, but for some parameters they produce the same solution, and now if your data come from the same solution, it is actually not clear which PDE this was generated by. So there's a huge uniqueness problem. So you have your data, but maybe this comes from a class of PDEs, yeah, but typical algorithms just produce one PDEs and it's not clear which one is chosen. Yeah, so the key question, I mean, we ask ourselves is, when does there actually exist a unique physical law for a given data set? And also, can we numerically check when this is the case? And yeah, I'm very happy to tell you we developed a theory in this direction. This is joint work also with Holger Boche, you might know from TUM, and one of my PhD students, one of my postdocs. So this theory should now guide you. If you're given data, when is it reasonable to apply this physical law setting? When do you expect a reasonable answer? So when do you expect uniqueness? Then we applied that to a situation where the question is you have robot joints and you would like to learn the friction law. Maybe you need that because you would like to, let's say, you would like to understand what has been, for instance, learned in Embodied AI, learned from a foundation model, but also here in this situation what we wanted to achieve was we want to understand better, so depending on the specifications of the robot, which frictions laws is obeyed, so that, then you can access the sensors in a better way and can ensure more reliability in the action of that specific robot, because for each joint, basically the friction law is slightly different. Yeah, so there will not be a common law for all of this. Every robot, every joint is has a slight different specification. And so what we did was we had two data sets. We had a data set which did not include any dynamics. It was a static data set. And there was a small data set where the robots were moving, the joints were moving, so this was a dynamic data set, but since you need a lot of time acquiring that, that was a much smaller data set. Then we had two neural networks, which we trained. We had a base neural network, which was trained by the big data set for the static effects. You see here the formula for the loss function, which we trained it according to, and then there was this additional network which also took the small data set into account. So you can view this a bit as a fine training. So like we would also for foundation model just train first, let's say, a coarser model and then a finer model with a smaller data set. The training was very benign. As you see here, everything worked out, beautifully. And here are a couple of numerical results. So what you maybe, let me draw your attention in particular to what you see here. So you see here a conventional model predictor. So this is this red line. You see here, it's very tiny, in green, our trained model. So this is already the fine trained model, predicting, let's say, the physical law, and you see here the measurements. And so you see the difference. So as compared to a normal model predictor, this approach, using neural networks in a specific way, you can do much better. You can extract the physical laws. We now have also results on, let's say, symbolic regression, where you can write down the law directly. So, from my viewpoint, this is a direction where, again, you can ensure more reliability. You can check whether, so how, let's say, the specifications are. You can incorporate that then also, for instance, in AI, which you use to guide here the robot. This is just one example. So this learning physical laws, I think, has a lot of potential. And as said, it is still unstable, but from our perspective, using theory, we are now on our way to substantiate that, to analyze which algorithms are better than the other, and then that way contribute to ensuring that this learning process is much more stable. So let me say, in the last, I see maybe a couple of minutes, also the sustainability issue. So we have many problems. I said reliability problems, use a lot of energy for the robots. So the question is, is there something maybe deeper lurking in the background? And so this is certainly, the compute itself, and if you think about it, most approaches just look at the software part. And I think also, as far as I know, also in the area of robotics, sure, you have embodied AI, but typically, the chips for computing And the chips for, let's say, training the AI, these are the custom ones, like GPUs. Yeah, but I mean, computing, I think, is something which we need to also take into account, and this is also one reason why things are not sustainable, and also why sometimes reliability issues can happen. Yeah, and so in that sense, I would like to now, in the last minutes, talk a little bit about, let's say, the perspective aspects, why the current, let's say, compute has certain problems and where the journey can go for the future. Also now, as you see here, to ensure that maybe we don't use that much battery power anymore, and in addition also that the hyperscale data centers maybe don't use that much energy. Okay, so we approach this from a perspective of, are there fundamental limitations we are maybe not aware of? And as said, we all compute right now on digital hardware. Yeah, so you have your GPUs where you train things on in all aspects of AI, cognitive and also embodied AI. But it could be that there are some problems which we're not aware of. Yeah, because you have typically continuous problems, you break everything down to zeros and ones, and this could cause certain issues. In computer science, there's this beautiful theory of computability, which helps analyze whether, to which extent on a certain platform, and here digital hardware is a Turing machine, and it's very widely acknowledged that everything what you can compute on a Turing machine, you can compute on your digital hardware and vice versa. Yeah, and so this computability theory helps understanding which type of problems you cannot reliably compute on certain platforms, like, for instance, digital hardware. If something is not computable, I mean, sure, you can run it through your machine, you will get an answer in any case, but then you have reliability issues, which is not what you want. So we analyze it from that perspective first, and I will come to sustainability in a moment. Yeah. What we unfortunately found out, and again, this is joint work with my dear colleague Holger Boche, is that certain problems, so you see here finite dimensional inverse problems, you can rigorously show that on a digital hardware, this is not computable. So this means there could be problems lurking in the background, which we are not aware of, but then, I mean, which leads to the fact that we now see these effects that, for instance, also people worked on it for a long time, but still, I mean, they are maybe not at the reliability level where we hoped them to be. And so here you see the rigorous statement. So here, for instance, this is an inverse problem, which appears typically in imaging sciences. You see a classical solver, and the main point I would like to make here is that you could make a systematic of one force, which is far off machine precision. So this shows that digital hardware has certain issues which we might need to take into account. And we have many results in this direction, maybe not going too much into the details there. For instance, classification problems, just computing the pseudo-inverse, solving PDEs. There could be what's called a complexity blow-up, so that the original, let's say, the data you put in and versus the output, one of them is then exponentially higher concerning complexity, also optimization problems, and so on and so on. Yeah, so digital hardware has certain inherent problems. That's, I think, the main message here. But you can solve this if you go to other types of hardware, like, for instance, analog computing. And also there are mathematical models, like, for instance, the Bloom-Schupf-Smale machine. And so there we could show that things become computable. So this points into the direction that maybe for certain problem settings, we might need to also rethink the hardware we compute, the chips itself. And there are very interesting directions in that respect. So I'm sure you've heard of neuromorphic computing. It's a type of computing which is closer to the human brain. It's also a more analog type of computing. Biocomputing, which is at the very preliminary stage. So for instance, in Australia, there are labs where you have real, let's say, living neurons, and you use that for computing. Quantum computing, which I think also everybody is aware of. And interestingly enough, I mean, neuromorphic computing is also much more energy efficient at the same time. So not only has it the advantage that it's an analog type of computing, but it is also more energy efficient. And so let me mention, for instance, this paper again by my colleague Holger Boche from communication. So what he did here is he compared classical, let's say, so here, what you see here is, so the classical NVIDIA GPU versus neuromorphic hardware from Spinnaker, which uses much less energy. And but if you see at the performance there even, the Spinnaker is even better to a certain extent in certain regimes. Yeah, so this points towards the direction that really novel hardware has an edge, both concerning reliability as well as concerning energy efficiency. It doesn't mean we need to replace everything, but I think it's a direction which is worth thinking about. And so let me also just, as a short advertisement, we also founded a company lately, Ecologic Computing, where we go in this direction. This is actually joint work, or joint with Holger Boche and also Frank Fitzek, who will speak in a moment, where the main idea is to, if you have certain problems from customers, then design optimal hard software combinations to obtain optimal energy efficiency and also reliability. So let me just spend the last few minutes talking about maybe where this new path can lead to, because I strongly believe that we are to a certain extent at crossroads, and we need to really rethink the way we do computing for the future. Okay, so this is for Neumann architecture. We all know how that looks like. Neuromorphic hardware is very different. It is more like the human brain. You have neurons, you have synapses, you have a lot of analog computing happening in there. It is, as I showed you, certain cases more energy efficient. And also, I believe what needs to be done is also for the future to have more rigorous measures for energy efficiency, and then also, let's say, objectively evaluate for different problem settings what is, let's say, the best hard software combination to choose. Execution speed is often considered more fast, and also robustness aspects. So what neural networks do we use for that? That's actually not a serious question, because spiking neural networks are the way to go. Neuromorphic hardware, if you want to go that route, are to a certain extent a spiking neural network. Spiking neural networks, as you see here, you have spike trains as input and output, and every neuron itself acts on its own. It receives inputs from other neurons, and it's building up a potential, which you see here. At some point, it reaches the threshold, and then it fires. Yeah, so everything is not synchronized. Time is an essential component. And so you can view this also in the following way. You can store information also in the time. And time doesn't cost any energy. Yeah, so this is also one reason why it's more energy efficient. From a, let's say, theoretical viewpoint to analyze it, it's very complicated. There are a lot of different models, like, for instance, the spike response model. And let me just say that we have now, work in this direction, where we, for instance, show rigorously that spiking networks are more, let's say, complex, more energy efficient to a certain extent than normal neural networks. But I think this is just the beginning of a journey. And I would also like to advertise here, we have now a big project between Bavaria and Saxony. We are very fortunate to get funding from the state ministries for science from both states, and this is joint work with my again, dear colleague Holger Boche from TUM, and with Stefanie Speidel and Frank Fitzek from the TU Dresden. And the main goal here is to derive, a theoretical framework for next generation AI green computing to obtain optimal hardware software combinations for maximal energy efficiency and reliability. And application areas, as you see here, are communication systems, medical devices, and in particular also robotics. And so let me also thank my team, which works specifically on this project, Next Generation AI Computing. Okay, so let me conclude. So from my perspective, reliability, sustainability are two main aspects which one need to consider. We are not, let's say, at the end of the line. There are many problems which you need to tackle. From my viewpoint, a mathematical, theoretical perspective is of essence there. We talked a little bit about explainability and also making things more reliable by understanding underlying physical laws of data sets. But then in the second part, what I believe is extremely important is to also rethink the hardware we compute on, to make it more energy efficient for many directions, also for the training part, also let's say then for inference. And analog hardware, analog AI systems might be a very exciting way to go. And so my vision for the future is really mathematically reliable and sustainable embodied AI systems. And with this, I'd like to thank you very much for your attention.
Wonderful, Gitta. Thank you. We have time for questions.
Thank you very much. A very interesting talk. I'm Shan Lu. I'm from King's College London. I work on robotics, especially sensing, tactile sensing. So I have learned a lot from your talk on neuromorphic computing, but most of the computation happens here. In central processing system. But for embodied AI or robotics, we have a lot of sensors, these edge devices.
Yeah.
So can you comment on how we can use your theorems and also your concept in processing the signals at the large level, especially for the sensors?
Yeah, so are you, thank you very much for the question. Are you referring to the second part, concerning sensors? So maybe I should say, neuromorphics, there are also already neuromorphic sensors. So for instance, here in Munich, we have Fortis, who has a neuromorphic section, so they are using neuromorphic sensors already. Which then, use much less energy, to acquire the signals. So this works for certain applications very well. So this neuromorphic direction, in the sensor setting, there are also neuromorphic hands already for robots. This is one direction, which I think is very valuable. It doesn't work for all applications. If you, let's say, need very precise data, that might be a problem. But if you can, let's say, live with a bit more coarser data, then neuromorphic hardware is, I think, a way to go there. The other theorems, so the first part concerning reliability, you can certainly use and apply that to make things more reliable. Yeah? So if you have certain constraints for robots, if you would like to know that maybe certain, let's say, areas are not extended, that you are within a certain range, then, for instance, this generalization bounds, this theory will ensure that you can, within a model situation, rigorously prove that you will not make a mistake. Yeah, so that's just in general the value of this rigorous, let's say, mathematical approaches. And explainability could, for instance, show you, if you trained your robot, and it made a wrong decision, let's say a wrong move, you can try to understand where it came from and then can retrain it. Yeah.
Thank you very much.
I hope that answers it.
And there's another question over there.
Okay, thank you very much for your very interesting talk. And I have two questions that corresponds to two parts of what you mentioned. And the first part, let's just consider a robotic that you want to make it complete one task, and roughly we would divide, if it doesn't work, roughly we can divide the error as two things. One is whether you plan the planning error and the execution error, like whether you plan a very good route to that part, and secondly, whether you really make your robot execute the action as you want it to do, right? So I was wondering whether your method could explicitly divide whenever there is an error. You can explicitly analyze which kind of error. Can you explicitly find what the error is, whether it belongs to the planning error or whether it belongs to the execution error? And is it possible to provide a theory regarding that?
I think that would be very interesting. I think thanks a lot for the question. As far as I know, but maybe I don't know, also Wolfram knows better. I don't know, explainability I think is not at that level yet, but I'm sure, one can do something in this direction. Yeah, I think it just needs to be done, but as far as I know, there is nothing in this direction at present to really understand, which of the areas maybe, which of these, let's say, processes causes the problem. but yeah, I think that would be an amazing, very, very interesting to do.
Okay, thank you. And the second question regarding to the neuromorphic computing, and actually I happen to be working on this area for many years, and well, I mean, we have done a lot of work similar to what you mentioned, that like firstly we want to like convert an artificial into neural network into spiking neural network and try to run it on some neuromorphic hardware to see whether it actually is energy efficiency, something like that. And it turns out that if you just convert the artificial neural network into a spiking version, I mean, theoretically, you might find it's somehow energy efficiency, but in reality, actually, we did not detect such efficiency. And then, like from our perspective, maybe in the future, you also mentioned in the last slide that eventually you should make it into analog computing, or you use analog devices to somehow mimic the neuron or synapses. This might give you the efficiency. And I mean, but right now, like Spinnaker or OIHI, all these things are based on digital hardware. And yeah, I'm not sure whether you would agree that eventually we should turn to this like analog hardware to do this neuromorphic. Otherwise, I mean, it's hard to detect such efficiency gain.
Yeah, exactly. So thanks a lot for that comment. I agree with all those points. I mean, current, let's say, spin cloud hardware has a lot of digital components still. In the area around Dresden, there are a lot of startups which develop now truly analog hardware, which I think go in a very interesting direction. But I mean, one need to see and monitor with this development is. So I agree. I think we need to go more in this direction to get more, let's say, energy gains. Although, as I said, I mean, my colleague Holger Boche, I mean, he showed in particular, I mean, for this one specific problem, which he analyzed that there is already for Spinnaker a small gain. Then you said that if you transform normal neural networks to spiking neural networks, you don't get that much gain. I think it's a question also how to do that. I believe that, I mean, if we now have, let's say, this new method of, let's say, spiking neural networks or wherever it goes, the algorithms need to be designed specifically for that. Yeah, and also the training need to be done for that. Some people use, let's say, spiking networks, move it to a normal neural network, train it there, and move it back. That will not give any gain, yeah, because I mean this intrinsic advantage of spiking neural networks is then destroyed. So in that sense, I think it needs to be, I mean, done in this, let's say, new domain. And what I believe is that what would be very beneficial is more a collaboration between also neuroscientists and computer scientists and experts from robotics, I mean, to really also bring more, let's say, what happens in the human brain more into the gain. Right now, I feel that these are two communities, but I think Oliver might disagree, because I think in Berlin, there is, I mean, I think also already a great collaboration between more neuroscientists and computer scientists, but I think I feel that this is a very, very exciting direction and could bring much more benefit in the future.
Okay, thank you very much.
I do have one question. I mean, when you think about embodied systems or robots, right, so this explainability is actually really cool because it allows us to identify what these systems maybe are doing wrong, right? But if you think about like a true embodied agent, you would expect that it is able to do some introspection as well, right? To understand like what is the reason why I'm doing something wrong, right? Or figuring that out. Do you think that we are on the right path towards this? Would these methods that you showed allow some sort of introspection for agents to maybe also do some active perception or exploration to figure out or to get new data?
I think that would be a very exciting direction actually to go. I mean, let's say if there would be internally running some explainability and then, let's say, online improvement according to the results which that gives, yeah, sure. I think that would be very, very interesting. I think these two aspects, like you mentioned. I mean, one is the robot itself in its environment, and the other is an outside human who would like to analyze, I mean, why a robot made a decision. Yeah, and I think for both explainability would be very, very well, yes.
Great. Thank you. Thank you, Gitta, for this great talk. This brings us to the next speaker Frank Fitzek. I hope he's online. Yes, he's there. Good. Hi, Frank. I'm going to move into the camera. Here we go. It's great to have you here. Frank has a telecom chair for communication networks at the Technical University of Dresden. His research focuses on cutting-edge topics such as 5G, 6G communication systems, quantum and molecular communication, novel computing approaches, human-machine interaction, and information theory. He's actually also a coordinator of two really large interdisciplinary projects, the Cluster of Excellence Center for Tactile Internet with Human in the Loop, CT, and the BMBF-funded initiative 6G Live, together with TU Dresden and TU Munich. In addition, he collaborates with GITA, as you saw in GITA's talk as well, on the GAIN initiative between Saxony and Bavaria. He has plenty of awards, the Danish Young Elite Researcher Award, the Nokia Champion Award, the Nokia Achievement Award, the Sapphire Order Research Grant, and the Vodafone Innovation Prize, and many more. He also co-founded several startups, so he's one of the superstars of the German computer science world or society. I'm super happy to have him here. Frank, we're truly looking forward to your talk.
Thank you. I hope you can see and hear me well. I'm sorry for not being there. I tried my best to come over there, but currently there's a lot of things to do, as you may know, in Germany for the excellence strategies and so on. I'm very pleased that I saw Gita before me because I think she gave an excellent talk about the topic that we are in. I will come from a little bit different angle. I still have some overlap with the slides, which is, I think, good to puzzle the things together. And I will try to explain a little bit what we are doing in the field of AI and where it is good. So originally, as you had heard, I come from the field of communication. And in a nutshell, AI is very interesting for us, but it's not new, right? We have put AI or neural networks into networks since the third generation already. So there's nothing new in the way when we use it end to end. So at the end user in the phones and so on. Currently, the debate of bringing AI into a full-blown network, that is interesting, and there are some challenges, right? I will also maybe think about some of the stuff that Gita comes, and then you will see how this all fits together. So now I talk about, I call it 6G Live Future Communication Systems, and don't worry, you only think about AI, but you will see what we are doing there. So first of all, 6G Live is a project that is coming to an end now with the first phase. There's a second phase envisioned for the next 4 years. The first phase was about 17 million, and it was more about the sixth generation of mobile communication system, as you might think, with use cases in healthcare and also with industry. We looked into some key performances like latency, security, sustainability. But from the day one, we had two aspects which maybe differ us from the other activities in the 6G field. There was technological sovereignty and digital transfer for society. And the second one is startups. So you heard about, we have a great interest in startups, and I will tell you a little bit about this later. 6G Live is a project, again, between Munich and Dresden. So Saxony, Bavaria is a very strong cooperation field. You might want to consider this. We have many things in common, but we are also orthogonal enough to really combine expertise from each other. Some of the numbers that we're doing, normally people look at publications. That's not so much from our interest. I just want to say that we have now 19 startups coming out of this project, which is quite great. We promised 10 startups to build out of a BMBF project, now BMFTR. I think that is unique, that a research project really promised to build up startups, and there's more to come, right? This was, the 6G Live was only the initial sparking, which said we would like to engage with them, existing one and new ones, but something else came out of it. I will tell you this in a Why we think about communication? Because you need a use case. If you don't have a use case, then everything is blown up. So currently, if you, for example, look into the world of robotics, and you see the caged robotics that are doing something, individual stationary robot, they are all wired, they have a hardware focus often, and everything is fixed and structured. The world is built for the robots, right? But there are new demands, and the new demands are faster changing products. So you have a smaller lot size, right? And you need more variants. I always make the joke, my brother works for BMW. In the last 20 years, they built the same car over and over again, and I buy it. But the only thing that they really change is the outer interior, the inner frame where the robots are, it's always the same, right? Nobody wants to touch them, it works. Now, for the future, that gives us a little bit a different world for robotics. So it's not one robot arm doing something alone. There might be multiple robots. They might be also mobile, coming together for certain tasks. When they are mobile, they have to be wireless, and there will be more software-based and AI-enabled robotics, as we can see it now. And everything will be dynamic and unstructured. So we don't only look at the big industry, we also focus on small, medium enterprises, where you cannot ask them to have a predefined working space for the robots. So the robots have to adapt to environment and not the other way around. Then I would like to introduce you to my biggest enemy in robotics. Or let me first show you some of these robotics we are talking with Boston Dynamics. We have this kind of Atlas and Boston Dynamics Spot. We are using them. As you can see, they have arms. You can bring them together and they can do something together. Currently, we have a platform, the Sphere, where multiple arms, up to 18 arms, can now work together on one element. So this path planning and so on is very interesting, but I'll come back to this. But now to my enemy, this is my biggest enemy. I'm not really a robotic guy. I bought my first robot in 2017, I think. And every time I just changed the wire to the wireless, every time the red button popped up and somebody had to press it again. Very annoying. The reason for that is really the control loop that you see here with actuators and sensors. And you have an input and output that will be controlled. And if this does not go well together, then it pops up. Depends on the robot when it pops up. Not all robots are the same. So we first tested out, we emulated errors, we emulated latencies to see when the red button will come. And that, as I said, is different from robot to robot. So in a nutshell, what we want to build in communication is something like a cable-like structure with low latency, no errors and whatsoever, and then the red button will never show up. So if we then come to multiple robots working together, path planning becomes interesting. So in 2018, we built our first humanoid robot with 2 arms and a head, also on the arms, so 3 arms going together. And it was difficult for us to not let the arms and the head crash together. And they crashed all the time. So every demo had a crash. And until we had really some people working on this path planning. And where's the problem? When they are mobile and they are moved together, you have a communication problem. It's not so much the control problem. It's about, if you have 2 robots talking to each other, you need one communication link. If you have 16 robots in the same area, you have already 120 communication links to each other. So this brings us to a little bit of a communication problem rather than anything else. Here, for example, you see the implementation that we have currently on the left. They're building together one piece. It's a generic piece of work. And there are some suspender where you can take an element and place it in the right place. And that they do already now for industry, for manufacturers, and so on. So that's quite interesting. You can even interfere with it. It's not a script. It's not automation. It's really, you can go with as you see the camera on the top, you can go between them, and they all will understand when to wait for the pause. And if you move yourself into these arms so that they cannot work with, they will just pause for a while until you are gone away. And this, we have done multiple of these kind of spheres now in a mini sphere on the right, as you can see. So this is something, I hope you hear the music. That is something, it's a 3-arm conductor. I will just move on. Yeah, the music is continuing. Wait a minute, can I stop this somehow? Not really. Can you maybe control the music on your side? You can't. Let me see what I can do here. Wait a minute. So now it's gone, hopefully. So this is a 3-arm conductor, as I said. The idea is really to use it for certain things. This is for music. There's a whole, the Dresden Symphonica played something. We are using it for the kitchen. This is a lab that we have here where people can go have drinks or a coffee, and then there are real cooks together with robots. So you see the human kind of interaction, right? And we are coming closer to the AI part, right? Because what the robots have to understand is what are the humans doing, what should I do now, and so on. So before I let you go there for the AI, and I think you're eager to learn about this, there's a little bit of 101 in communication, right? So if you want to replace the cable, then you can do this easily by different techniques, 5G, 6G in the making, right? Or Wi-Fi, right? Why not using Wi-Fi? So in general, in a nutshell, don't use Wi-Fi. Wi-Fi is a listen before talk technology. That means that you don't have any deterministic latencies, right? And this is what we need in robotics. 5G, 6G are centralized reservation-based systems. There you can look into deterministic ones, especially if you combine it with network slicing or TSN approaches, which are now easy to have, and we're dealing with them. Currently, TSN is on network slicing is also important for us if you want to have multimodalities. So when you have human sensors like audio, video, and haptics, you need different latency bandwidth requirements. And if you put them all in the same base, then this is a problem. So point-to-point is already a problem. So replacing the cable is a problem. To make it more complicated, what is if you have multiple robots going around, right? So this is especially where Wi-Fi is also a problem, because now the access delay will increase heavily, and they will fight over the channel while the centralized systems are not doing it. Wi-Fi is currently also looking into this, because they would like to have different strategies, but as they are using the ISM band, which is free of use, and this is nice. On the other hand, you need to use listen before talk. You cannot use reservation-based. Now, the other thing is, what if you don't have different messages, if you have the same message you would like to convey to them? I will come later to an example where we need this. So if you think about the old radio, that was given, right? If you transmit the information, everybody would have the information at the same time. If you do this on the IP level, it's not like this. So reliable multicast is something, it's standardization of ITF for a long time, and there are different proposals how to do it. We implemented there several solutions based on random linear network coding in order to realize that. The other thing is, why do we really need, let's say, a planned network? Why not a fully mesh type of networks? Like drones in the air, they're flying there. You need a network that flies with them, right? But even in robotics, where they're moving around and they need somehow to maintain a network, why they do it themselves? There's something that we do with a startup called Meshmerize, where the industry really adopts this very quickly. And this is interesting. You can use it on Wi-Fi as well as on 5G and 6G technologies. It's more the routing based. And in order to make it resilient, they're using multi-pass, not a single pass. So if one robot goes out or dies out of battery, you don't lose your connection, or you have to rebuild the connection in 30 seconds. Now here, you always maintain it as long as there's one pass aligned. Then, as I already mentioned, that we have this kind of startups and this interaction between Bavaria and Saxony. Here you see also LMU with Gitter in the GAIN project. And we have a lot of technology projects on communication, robotics, quantum AI, but also the kind of startups are important. And why are startups so important for us? That many reasons. One of them is to keep our PhD people somehow motivated, right? What they really would like to do after they do the PhD. Unfortunately, we are so successful. Some of them, they don't even wait for the PhD. They just go and jump for the startup currently. And what they do is they really focus on one topic, as you do in your PhD, but in a team, and they're very fast towards drilling a deep, deep hole, right? And that is interesting for us. The nice thing is also, because they are so fast, and if they have their own funding, they can order hardware faster than we can, right? So the development cycle in the startup is way faster than in the university in some aspects. On the other end, they also run into problems, and then they come back with real world problems that we can solve in research. So this give and take between really academia and startups is something that is really interesting for us. Just to let you know what we're doing there, and to give you a hint, here we have the Launch Up 42, which came out of the 6G Live project, where the BMBF at the time, now BMFTR, said they would even pay us a small team of 5 people, and they will check the startups for financial plan, for graphics, for product design, and giving them a small home, as you can see here. That is this container. It's very small, but the startups are using it for meetings, for meeting their investors and so on, and also to meet each other, to exchange that. And the more startups we have, the easier it is for us to have success, because you collect the errors the others made, and you motivate each other if it's not working well, and you exchange not only people, but also maybe some experience, or combine your products. And you always have the university as a backup, right? Which is also very good to be very risky in your research. So here are some of the startups. You can even look it up. If you go for Launch Up 42, you will find that. But now to your topic, AI, right? And it was not always called AI. The original term, as Shannon and Turing coined it, was artificial thinking machines, right? I like that a little bit more, because they're still machines, right? It doesn't give it the human touch so much. As we call it now AI, the question is, what is AI? All the people think about this, right? Nice things, make me some pictures, make me some text, maybe for robotics is good. Is there a real use case? And often you hear, oh, in medical, they find cancer faster than the humans. So pattern recognition seems to be something that they can do. But I would see it from the engineering point. AI has to do with data, with computing, and energy, right? And there's what Gitta also said before. But data is, first of all, you have to collect it. You need the right sensors, right? Currently, we're building also digital noses to get some more insights and learning skills. You have to store them, and you have to communicate and transfer this kind of information, which in a nutshell comes back to the energy part, right? So if you now look at the use case, I always said if you don't have a use case, then you don't have a new technology. And people in 6G now, they always ask, what is the new use case? Because 5G had already all the use cases, the technical ones. But for 6G and for all the technologies we are building in robotics whatsoever, there are some grand challenges of the 21st century, right? I showed it here a little bit dramatic with the waves. The pandemic, we all remember it. Some of us has even forgotten that there was something like this. But we have to deal with it if it comes back, right? The pandemic is something we have to think about. The aging societies, together with the skill shortage, by people getting older, somebody has to take care, and we don't have the expert anymore, right? So the robotic part will play a bigger role, but also climate change and geopolitical challenges is something, right? So we have to build solutions and technologies that address or keep in mind what kind of challenges we have currently. So if you look at this, there are for me some designing rules. One of the things for the solution space is trustworthiness. And trustworthiness is a very big topic. And if you talk to engineers or to other researchers, there are different aspects of trustworthiness. So technology-wise, if you look at the human-machine interfaces, how real are the sensor data that you get? Is this good enough, for example, right? Then if you convey data, network of networks, what is about latency, about jitter, about error probability? In robotics, as you see in our kitchen, if you're a cook, the first time the cook was in the kitchen, you always looked at the robot above him. Will this robot hit me or not, right? It's a good question. And that brings me on the left side where the humans are. They have a different wording of trustworthiness. And if you move into the digital worlds, like with goggles or in caves, then you will understand what is real. And what do we understand? And trustworthiness you need this to really address pandemic, aging society, and the skill shortage. If you don't have that, then you don't have a good solution for that. I don't know where the music comes back, but let me see. I don't know how to do it, honestly. Let me see how to do this. I have to go there now and to, you know what? I just kill it. I might come back. Wait a minute. There we are. Sorry for this. Now I have to go here. Wait a minute, that comes later. So there we are. I hope you can see it. So the other thing is technical sovereignty that I told you in the beginning for 6G Live, where we really address the geopolitical challenges. So does it mean we need to find solutions that we have in our hands, right? Europe is now looking into building their own chips, their own solutions, etc. I will show you one example later. And then there's sustainability. A lot of people talk about this. There was always green ICT, but now the electrical bills come so big that people will say, oh, we have to do something about it. Now, I think that Gitta pulled you through these slides, right? We're saying, hey, look at the data that goes up and that we have a problem, right? And the two people that helped us to understand the problem are Shannon and Landauer. So Shannon, the guy who gives you the unit of the bit and the limit of a capacity of a channel where to convey information. I come back to this. And Landauer, who said, what is the minimum amount of energy you need if you have irreversible computing and a digital platform, right? And if you then multiply it with the amount of data, Gitta showed you this, it crashes with the world's energy production, right? You can do a little bit if you look into platforms like NVIDIA to have accelerators on the digital platform. That helps a bit, but it's not really making the solution space so big. And there are some solutions like Google said to buy nuclear power plants for the AI data centers, or this guy who said drill baby drill, right? Where they spend 500 billion now, 300 billion for energy and 200 billion for the same hardware. So they don't think in a disruptive way, they think of the same, only scale it, right? That will maybe help for a while, but not that much. The other two things, and Gitta told you, is Turing about what is really computable and what is real, coming back to the trustworthiness problem. And for us, if we have human-machine interaction, Albert Einstein with speed of light is how fast can we exchange really information? So latency is a problem there, right? And I make this a little bit faster because Gitta told you this. For us, it's not really the evolution of the same. We would like to have more disruptive ideas, and I will show you some of them that we are doing. So new ways in communication. So Landauer said the energy, but Shannon told us there's a certain capacity that we can have, right? And this capacity only depends on the bandwidth you buy and the SNR, the signal to noise ratio. That's so easy, the equation, but this gives us a limit and nobody can go beyond it. That is true if you look at it from the engineering perspective. But if you look at a little bit further, there is something, and they already knew it, that was called semantic or goal-oriented communication. So just to give you an idea, the classical way of conveying a message was you take the message, you give it to the sender will convert the message into a code word. The code word normally takes out the redundancy of the message, but puts more redundancy on, intelligent redundancy, to have a code word that goes over the channel. And even though you have bit errors on the other side, you get a distorted code word. But with the intelligent redundancy, the receiver might be able to estimate the message. And that is classical challenge to say, the receiver asks, what did the sender tell me? Okay, so this is what it is. And in order to, if the sender has, let's say, 5 messages, as you can see here, we will create the code words that they are orthogonal. So once we have the code word, we make sure it's exactly that. And even with the distortion, we should be able to retrieve it. Only if the distortion is too much, if the signal to noise ratio is bad in the equation, then we are jumping in an example of the green point, maybe to one of the other points, right? That is classical. When we change the way to semantic or goal-oriented, we don't ask what did the sender want to tell me. I only listen to certain commands, right? So for example, as for the robot, should I stop? Should I go to the left? Should I go to the right? These are the questions he has. The rest is not interesting for the robot at the moment. So the sender will take a sender ID, which is a code word what they both agree on, and selects out from this sender ID a random code word. And this random code word goes over the channel. It will also be distorted in the same way as before. There's no trick in that. And then the verifier will say, is this the message or not? Okay, so that is the idea. And when you do that, then you see that now the coding spaces are not orthogonal anymore. They are overlaying. And by overlaying it, you have a new capacity, right? That sounds great. So if I have here the ID 24, which is a message, and I select a random code word that is in this set of this space, let's say like this, then you convey it. It will be distorted a little bit, but it will be still part of the code words in the ID 24, and my receiver will say, oh, that's my message, all fine, right? So when you do that, then you can say, as each ID has a code word and it picked up randomly, we can say they overlap, they're not convex anymore, but now we get a new capacity. So in a nutshell, and how it works, it's by Alswede in the 80s already, but they said the number of messages that you can create grows exponentially following Shannon with the number of bits per message and the Shannon rate, something between 0 and 1, right? If you now move to these overlapping space that I showed you before, the number of messages grows double exponentially, which is way more. So this is really good for latency as well as for energy, as I will show you in a minute. But you also might say, wait a minute, that cannot come for free, right? And it's true, it doesn't come for free. For example, I told you the example, I take one ID, I send it to the other side, it gets distorted, but I still say it was ID 24, right? But what happens if the distortion is so big that I end up in a different coding space? Then I would identify as a different one. If I say it was not my ID, and I would make a mistake. So it's red and said this was not mine. So this is distortion, but this is in the classical way more or less the same, right? So when you are waiting for ID 37, right, and the sender sent ID 24, but the distortion is so big that you wait, then you would say it's mine, but it's not. So this is a different type of error. This is what we call a type 2 error. The other one we call type 1 because it was always there. Type 2 is the new error we get, and this is because of we overlay and we have some misunderstanding of the idea, of the understanding of the idea. Later I will tell you how it works. And because of that, this understanding of yes and no is not the correct. It's more a hypothesis testing of saying no is easy, but yes is difficult. So it's no and maybe. That is the difference now, right? And where does it help, no and maybe? I come back in a minute to that. So first you will ask, how can I create something like this? So the whole ID exchange should go over a noiseless channel. Once this is done, we are fine. Then we send the sender ID, we give it to the other side, and then we will say yes and no, or in the new way, no and maybe. The problem is, where do I get a noiseless channel? Do I need a cable? No. Here we use the old Shannon transmission. So now we assume that Shannon takes care of the noiseless channel, and we need codes. And he told us in theory there is a code that can do it, and he didn't tell which one. But there are better codes, and there are also now rate-achieving codes like polar codes or network codes. And then you see, okay, the sender is now consists of the ID encoder and the transmission encoder. The transmission encoder is classical, the old Shannon one, right? And Then if you draw a line here, then over the red line, you have you make type 2 errors, and under the line, you make the type 1 errors. So this type 1 errors are classical, type 2 is new. But if you have more errors, but a new capacity, the question is, will this add up in the end or not? Or what can I do with it? And what you need, two things you need for that, the local randomness. So I told you, you can select code words randomly, and that is better than deterministically. Deterministic, you can also do it, has different properties. Then it does not grow double exponentially, but it grows faster than the old Shannon one. When you have local randomness, then you also have to convey it to the other side. Better is you have a common randomness, for example, by exchanging with quantum entanglement some kind of randomness, which we call random randomness, or you have an ID. If you use pseudo noise, then you have a seed that you exchange beforehand. Now, if you ask how is this really working, it works like any classical code. You take your information message, which has k bytes or k symbols, and you just code it within a encoder matrix, and you get n bytes out of it. And n is bigger than k, right? That is normally what a code is doing. The encoder matrix, whatever you use, we often use random linear network codes, just we fill it with random parameters. That will work. And what you get is then a classical code word, and in the Shannon world, you have to convey n times the symbol. So in this case, we have 256 bits, and this means, so the field size of 2 to the 8, sorry. You have 256 states in the symbol, and this multiplied by n, this is what you normally have. So n log q is then the number of bits you have to convey in a classical way. In the new way, what we will do is we look at the code word, we randomly pick one tag and take only one symbol and send to the other side, this is my random position, and this is the value. And now you understand how it works. If you will get this two tuples, you go to your code word and say, is this one of my messages? And if you don't find any, it's no, and you are out. If you find a code word that has it, then you might say, maybe it's mine, but you don't have the full code word, and you may want to ask for more information, and you wait. But the good news is, those robots that are not interested, or they are not meant by the message, they are out by one symbol, or one symbol and a position, right? If you have common randomness, you don't have to send the random position, then you get this one for free. So for example, this would be one tuple, or this you can send. There are different codes in your space. And what can you do with it? We have applied this one, for example, for voxel-based semantic compression. So you take the classical one, if you're familiar to this, and then we wanted to try to understand what is this kind of object onto the other side. And on the right, you see the compression and transmission latency, and the best is the better you are to the left, right? And when you see where state of the art is, and if you now use this post-Shannon for control, then you see we are way better off in just sending semantic ones, because we know very quickly what we want and what we don't want. The same you can use, for example, for a ball balancer. Here we look at the area that you balance the one, and what you look at is the robots will understand right away, it's not me, I can stay where I am because I got the ID, it's not mine, and the other one will listen a little bit further and this, maybe it's me, I'm going up, right? He makes a guess. And if he finds out why the transition go, it was not me, he tries to repair it, right? And then we look at the area of the ball balancer. And is post-Shannon something interesting for 6G? And there are some activities from Huawei. They are already pushing this in 5G. They tried already, now in 6G, they're pushing again to understand how can I use this one together with a trained AI model. That is quite interesting. We use the same for the metaverse information. If you're interested, just look it up. New ways in computing. I think Gitta told you something about it. Instead of just staying to the digital world, analog, biology, and quantum are options. We all of them have them now here in the lab. And the hope is that going to analog, we get a factor of 1,000, and to going to biology, so brain cells on a chip, you get a factor 1 million. The problem is the learning time, right? So you would need something like days to train the biology one, but then it's very quick and also has energy. The last thing about trustworthiness is in analog, as Gitta said, that our colleague Holger Woche, he proved that you can do it, right? Analog is trustworthy, not using a Turing machine, but a Lumschub-Meyer, but in biology, we don't know it yet. So there's research to undergo. And some examples here, what you see here, for example, is a new feed, a video feed of a drone. And we are training it now with digital and also analog things and trying to understand what we can do it. This is, for example, SLAM together with Gaussian splatting, right? And once you do that, you can, for example, fly the same route or any other route. And I think for some new use cases, we can use it. Here's another example, and that is bringing me towards the end. So normally, if we want to send a picture, right, to tell the robot move to the left or to the right, we give a 4K picture. So the source has this. In this case, it's a indigo bird, and the question is, when does the receiver know it's indigo bird? Do I need the full picture? Or think about progressive PNGs or JPEGs that will grow with more information you get. After a certain while, you can detect with certain probability this is an indigo bird. You can see here the scans. After 1.5% of the data, we would say it's a shower curtain, right? Then maybe with 3%, it might be a wall clock. All not correct. But already with 4.6%, we know it might be an indigo bird. The probability is not high. Maybe not high enough, we wait a little bit and we get more and more scans. And of course, only if it's the full picture, then you have the highest chance of guessing it. But if you have to make a decision, for example, in robotics, sometimes you have only a certain time. And after that, you make the decision. That's quite interesting because then you can already do something. And this idea, together with the hypothesis transmission in post-Shannon, is more or less the same. We are getting parts of the information and we try to make an assumption what was the message. So it's not classical transmission, it's not classical vision, but it's something new in it, and this is something very interesting for us currently. So the last thing, how to implement AI into the networks, we have certain setups here. One of the things that we are building together with some startups, there are 3 startups involved, all in the 6G hubs. And these 3 startups, they made a 5G core, a 5G RAN, and the radio units. So when we talk about technological sovereignty, when it comes to software and hardware in the front end, everything we can do out of Germany already, right? And we now need the computing platform, which is in the form of the Raspberry Pi. We talked here to people in Dresden and others. They could also build it. Currently, it's cheaper to buy it on the market, but we could do it. And the reason why we built it is not so much that we wanted to show that we can have the technological sovereignty. The nice thing is that we now have a full-blown system that the startups can sell, and we researchers have an innovation platform. So when we think about post-Shannon, where do we implement it? Or your AI, where you really place your AI, right? Normally you will place it outside in the cloud system and use the system just as a dump pipe. But if you look at cooperative SLAM with Gaussian splatting, how many elements there are, you can nicely split them over the network. And you put them on the placement of these elements is so important based on latency and also on bandwidth. If you move everything to the cloud, backend cloud, then you have to transport a lot of data. That takes time. But if you have a look at the data at the device, then you reduce magnificently the data rate and then do the rest in the network. And you place it where maybe your computing delay is the smallest. So this is something that we can do in the network, but it's a tuple out of the use case, the AI, and the AI, how much it's modularized and how much we can spread it. Okay. With that, if you want to leave something, there's shamelessly PR now for the new book where everybody worked on it. There were over 160 people contributing to it. There's some of the ideas that I just mentioned also in the book. With that, thank you very much.
Thank you for this inspiring talk. Are there questions? So
It was crystal clear.
this was Christian. No, I have a question, Frank. I'm also reading this thesis from your group right now, and will be done in 1.5 weeks. That's my promise. So they are also like you basically show like how communication can be improved on robotic platforms. So where do you think are we right now, and where might we be in the future when it comes to getting more efficient networks on the platforms themselves?
So the communication architecture is quite interesting. If you go to the fixed networks, you have already all the degrees of freedom together with software-defined networks, network function virtualization. So the placement of intelligence in the network is easy. We have to break up the mobile networks because they are very stubborn. They're the dinosaurs. They always think in the same, right? Where can I make more voice coils, right? Or a little bit of data. The placement of computing will be important for us. It will be one of the major things, especially if it's not only placement of the same type. If you look at accelerators of different types, analog and biology, for example, then it will be also interesting who makes the decision in the network where we spread the tasks. This alone is could fill up hundreds of PhDs, right?
I mean, when you think about humanoids, for example, right? Actually, you want to get rid of the cables because they are pretty bad for movement and so on and so forth, right? So ideally, you would have an architecture where you distribute computing over the platform and also have communication between the platforms, right? So how much, or what is the pathway to such an architecture or how long is that getting kind of like an optimal architecture for these type of decentralized computing infrastructures on these humanoids, or could even be cars or so?
Yeah. So as I said, we are currently trying to build it and give an example for the standardization bodies and say, look at this. There are some activities to enable us for computing within the mobile networks. So, for example, if you have heard in 6G, the RIG, non-real-time and real-time RIGs, there will be some XD and R apps that you can now already use and implement something. It's not the best way, but it's a starting point, right? And that helps us to distribute. The thing becomes even more, so one thing is really offloading, right? Take the computing away from the mobile robotic platform because you save energy. But even there, it's a trade-off, right? If you have to send off a lot of data, so a little bit of computing you leave on the mobile robot, but only to compress the data, and then you send it over. Mm. But what if you have multiple mobile robots? So where do you compute it? So maybe they have a common task. Then maybe you could say, hey, I calculate it more centralized because I know both of you and will do something, but the placement will be interesting. And this again is something that we have to envision. We build it up in test beds, but we need also the big companies to understand it. So if, for example, the next platforms are not built by us or by others, then it's tricky, right? On the positive note is that everything is softwareized and we could do it also easily now.
Wonderful, thank you. Any additional question? People are starving for coffee, I think, right? Frank, thank you very much. Thanks for doing this, and thanks for attending this workshop. Thank you.
Thank you.
We will have a coffee break now and meet again in, what is it? Let's go for a compromise here. Would be, let me see, 11:10. Is this good? 0. Here we go. Yeah, thanks for coming back after the break. Breaks are always difficult because it's so great to interact also, right? And having great food. So what we'll come to this final presentation here, followed by a podium discussion, actually, which will be right after that. We will also take another group photo, right? Because we have different speakers today. So we will clean the stage and then put the chairs on, and before the stairs are on the stage, we will actually have another group photo. And but before that, we will have Jens Bailey talking here. He's a postdoctoral researcher and a lecturer at the Department of Photogrammetry and Robotics at the University of Bonn. He also got his habilitation from the University of Bonn on the topic LiDAR-based spatio-temporal scene understanding for autonomous vehicles. I figured out just by reading his CV that we are actually scientific siblings. We had the very same advisor, Dan Kremers. Like he finished in 2014 and I finished in, I think it was 91. So not everyone was born by then, right? Yeah, and you will talk about LiDAR point clouds generation of urban environments, and we are looking forward to your talk, Jens. Thanks for coming.
Thank you for the kind introduction and also for the invitation to present some of our research. So we have very different topic areas. We are mostly also doing agricultural robotics, but we are also doing embodied AI or robotics, how we call it. And specifically, we are also interested in scene interpretation. So, and particularly, we are interested in scene interpretation for allowing such embodied AI vehicles, self-driving cars to drive around. So, therefore, we are looking into approaches how to make this possible, and because, as you might imagine, such a autonomous vehicle needs actually a good understanding of the environment. It needs to understand where it can drive, where it cannot drive, maybe where are other street agents around, and has to figure all this out to do actually driving. And since I showed here a Waymo car, it's actually already possible in some parts, but of course the vision is that we really get to level 5 autonomy. That means that you really don't need a steering wheel or any operators anymore, but can drive everywhere around the world. So on the left side, you see our vehicle that we also showed last week to some people. So I think Oliver also saw it in person. So this is just a 3D rendering. So this is our sensor platform where we have cameras mounted on and LiDAR sensors, which we can drive around and collect data ourselves, which is a good thing because we can collect actually a lot of data, which is also needed to do scene generation in the end. And as I said, all vehicles are equipped with a lot of sensors, like cameras and LiDARs are the main sensors, but also radar and also GPS and so on. But in particular, we are always interested in doing scene interpretation using 3D LiDAR sensors. In particular here, this is the Auster sensor with 128 beams. And I'm not sure how much people are aware of how a sensor works, so therefore just a quick introduction what it looks like to use such sensors. So first of all, when we are talking about the sensors, we're usually talking about that we have this automotive sensors which really can generate at real-time speed nice point clouds. So they have multiple beams, and usually when we are talking about the sensors, then they have a certain vertical field of view. And they can produce the point clouds that I will show on the next slides at a speed of 10 to 20 hertz. And that's of course important when you want to do real world driving, because you need to react to the scene that is happening around you and with fast moving cars and everything. So from the principle, you might imagine how it works inside is there's an emitter that sends out a LiDAR beam, then it gets reflected from some surface, and then there's a detector that detects when it returns. And taking this 2 times, you can then deduce from this the distance. And this is the principle behind it. And usually this LiDAR beams are emitted around eye-safe visual spectrum of 990 nanometers to 1055 nanometers. So therefore, they can also be operated in just a normal environment and don't hurt your eyes. So what is internally happening, it's not only emitting this once, but it's emitting this for every beam, and the beam is rotating. And then it looks something like this, that you get something like this range image out. So you have for each of these different beams, so colored by different colors, you have then for each direction that is shooting, basically the distance. And then taking these distances and the known sensor geometry, you can then turn this into a LiDAR point cloud, and then it looks then something like this. So this is a visualization with the sensor in the middle, and this is actually a scene. Oh, it should play. Okay. Oh, that doesn't work. There's actually. Okay. Okay. Before it worked, but. Whoa. Is there some setting that I need to do? But anyway, so what you should see. No, okay. Just as the support is arriving, it works. So what you should see, or what you see, is basically the rotation of the sensor with the beams, with the 128 beams in this case. And this generates this nice point clouds around the sensor. And we want to take this point clouds and do something interesting with it. But what you also can see is that maybe here in the back you can see the the building around it, but here also some street environment. This is one single scan, but what you can also see is that due to the sensor geometry, it gets also very sparse around the sensor when you're going farther away from the sensor. So this distance-dependent sparsity is basically a big problem with the LiDAR sensors that you have to account for somehow. And therefore, our idea was, how can we maybe use these sparse LiDAR scans and make them dense? And this is the first part that I want to talk about, how to turn sparse LiDAR scans into dense representations of the environment, because the denser the better, we have more information about the geometry. And the second part, and I'm looping back to what I introduced in the beginning, that we want to have a semantic scene understanding, and therefore I'm looking also into how to generate semantic scenes. So here on the right you see basically a point cloud, and the semantics are indicated by colors, where you can see the street in purple, the sidewalk in dark purple, via vegetation in green, and yellow is buildings. So, and this is what we want to generate, and this will be then the second part of my talk. But the first thing, of course, how do we do scene completion? And here, as I said, the input is a sparse LiDAR scan on the left side, and ideally we want to get out the densified point cloud on the right side. So, and as you can see here, we are doing a lot of work. We are removing the dead, so the invisible part around the car, because the sensor is usually mounted on the car, and therefore you see also here the shadow of the car into LiDAR point cloud. This we want to add, but we want to add also scene geometry and scene detail, as you can see here in this representation. And of course we want to do this faithfully in the end, so that we really get a good representation of the world. So the question is now, how do we turn the sparse scan into this dense representation? And our idea was to use the novel generative AI technology that was also used for image generation, the so-called diffusion models, where we can basically take as conditioning the sparse scan and then turn this into a densified scans using this diffusion models. So just as a short reminder, probably many people of you already read the paper, but just to give you a basic idea how diffusion models work. So we have our initial scan, from which we generate a noisy version. This is then resembling some known noise distribution. And then we have some denoising steps that are shown on the right that turn this into a dense scan. And usually this is done in a process as this, that we take our initial scan, and then we're adding gradually noise onto the points, and then until we get to a known noise distribution, something like a Gaussian or something like this. And then what we want to learn is basically then the backward process, so the noise prediction, so that we can go from one step to another by predicting what noise was added before. So this is something that we can then learn. So we are learning for each of these different noise steps, what was the noise that we added on the original scan in the end. When we look at this process, then there were already some prior work doing this. And usually how it was done before is that we take all the points that we have, so this is the conditioning scan, and then we're adding to each of these different points the same noise in the end on top of it. And as we found out in our paper that was also presented last year at CVPR, is that this is not the best solution that we can do, but that we can do it much better when we are adding noise to individual points and make this then also specific for this area. And I now want to get a little bit more into technical details before I show some qualitative results, and then hopefully I'm not losing all the people here in the audience. So anyway, we have this input scan, and the first question that you have to ask yourself, how do we get the training data? How do we get the complete scan? And the easy idea that you can exploit is that you have this car driving around, so you're recording multiple scans together, and these multiple scans you can then just aggregate together, and from this we are getting the dense scenery that was recorded by the car. And this is the so-called ground truth point cloud that we are using for learning. And our goal is now to learn the diffusion process to produce this ground truth point cloud. And we do this in two things. We have to learn this noise prediction. As I said, we turn this point cloud into this noisy point cloud, and then we try to predict for each time step, which we can sample, the noise that we added in this step. This is the so-called unconditioned part of the generation pipeline. And then we want to condition it basically on our input scan, and for this we have then to learn this conditioning. And the conditioning is happening via a different encoder that is taking the input point cloud P and turning this into a conditioning, and this conditioning is then used to learn this conditioning process. And putting both together, we can then generate with this conditioning conditioned point cloud. As you can see, this is still not the thing that we want to arrive at, so you will see that it's still not that dense. So therefore, we have a second part where we are having a refinement network that just takes this generated scene and just refines it and makes it even denser in the end. So and this is just a normal convolutional neural network that basically takes the neighborhood of points and tries to predict other points via offsets. So that means we are turning this m points that we get out from the diffusion into k times m points in the final point cloud. So to make this a little bit more visual, what is actually happening there, here's an example of the complete approach. So we have this initial point cloud here. This is our conditioning scan. And with this conditioning scan, we are now, okay, it's now again the same problem. Okay, it's playing. So with this conditioning scan, we have then the forward diffusion process. This is basically adding the noise to each point. And then we have the denoising process that is basically removing then this noise again to complete the scene. And then we have our refinement that actually then does the whole magic to turn it in a very dense scene. And this is then giving us the scene geometry. The interesting part is now when we compare this qualitatively, for instance, to other approaches, then we can see that we are doing a much better job in the end. So we have here some traditional approaches that just use some offset vector predictions as we do in the refinement network to produce the scenes here. And then you can see here the result from our diffusion process here in the lower left. This is the already completed scan, but not that dense, and then the refinement to make it even denser in the end. Also, quantitatively, we could show in our paper that this already leads to much better results. And as I said, we compared it again to traditional approaches for scene completion that are using just the information from the scan. And here is shown the camphor distance and some distribution metric that basically measures how similar this looks to real scans. And then here you can see, compared to other point diffusion approaches, we are also getting much better results in the end. So with this high-level idea, I wanted to close this first part. So we can now turn these individual scans into dense representations by using a diffusion model. And the key idea was here, or the key novelty of the paper was that we are using this local point distributions, and that makes it possible to do this also very accurately. And we can operate this also on real-world scenes, so we have also some data that we recorded with our car, and then we can even transfer it to this and complete the scene even using a different sensor geometry. And in the end, it also, of course, for the paper worked out better than other point diffusion methods. So, but it's only one part of the equation. So we have now a dense scenery that we can also then use to maybe sample different viewpoints from, but we still have not the semantics in there. So this is the second part that we did, is how do we get more annotated data? And this was the idea that we are combining what we had before, that we can generate the dense scenes, but then also combining it together with the semantics. So before we start diving into this approach, so the traditional workflow, basically, as many people use, is that we have our recording platform, record a lot of data, then we have this aggregated scans, and then we annotate this. So, and from my personal experience, I can say that this is a very tedious process, and you don't want to do this every time you have new scenarios or you want to cover new scenes. So therefore, we want to get rid of actually doing this annotation work ourselves. So, and the idea here was that we now try to develop an approach where we take basically our annotated scans that we maybe annotated with some help of some company or by students that we do at the university, and then take a generative approach that we can just sample new examples here. So, and hopefully we are doing a better job than ChatGPT generating a cube or a dice, because as you can see, it did not the perfect job here. But we try to generate nice scenes that are then also novel in the sense that they are providing new scene geometry, so novel street configurations, but also look realistic in the sense that we can also use it for augmenting our training data or generating training data that we can train our scene interpretation approach from this. So again, the same pipeline as before. To get the ground truths, we are now aggregating basically the scans that we annotated by hand, and this gives us the ground truths. And for this, we use, for instance, our semantic kitty data set that we already had flying around and that we can use for getting nice scene annotations. Then the thing is that we now cannot, or we don't want to rely always on conditioning, because then we are not winning anything. Before we had a real scan and we want to complete it, but in this case we want to generate completely new scenes. So that means we want to have something that just from the latent representation can generate new scenes. And for this case, we now have to use a mechanism that basically allows us to sample this new latent to turn it into scenes. And therefore we don't want to rely that we give it an annotated scan to give us a completed annotated scan. We want to generate new scenes. So therefore we have now to use something like a variational autoencoder. And the autoencoder learns latent representation that has a known distribution. So, and this latent representation with a known distribution allows us to sample new samples because we know the probability distribution. So that's the thing with the variational autoencoder. So that's the variational part. The autoencoder part is that after this process of this encoding with phi and the decoding with psi, that we want to have the same scene back. So this is trained on training data. But as I said, the important part to remember here is that we are basically interested in getting this latent representation here. And here we make one step that we generate first from the scene this sparse representation as shown there with the calligraphic Z and turn it into a dense representation. Then this is used by the decoder. In the end, we are just interested in the decoder. The encoder is thrown away. It's just for the training. Good, so that's the first part. And as I said, to make this possible with the decoder, we have now to deal with a problem that we generating this voxel grids and this very dense voxel grids. So for the encoding part, this is not a big problem because we are starting just with the scene voxelized, and then we have this encoder part which reduces the spatial distribution or the spatial resolution of the grid. But for the decoder, this is a problem. So therefore, we came up with a clever idea that we have now our dense encoded latent representation as voxel grid and use in between pruning layers that only refines it to the scene geometry that we are interested. So we don't want to keep this dense grid all the time. So therefore, in every step, we are taking just the parts that we are interested in, so where it's not free space, for instance, predicted, and then just focus on the parts where we then want to generate and upsample it further. So again, we have the basically downscaled version of the scene, and then we want to upscale it again so that we get the complete nice point clouds out in the end. And this is one instrumental part in the whole pipeline, this pruning in between that makes it possible to do. And makes it also memory efficient and also possible with university GPUs to train. Exactly, so the process is now as follows. So we have our scene, we have our encoder, and then we encode our scenes that we have annotated. So this is a training data. And then we train again this diffusion process to turn this latent scene into something new in the end. And there we are using the same principle that we had before. We have now this latent voxel grid, and then we want to generate, we put noise on top of this latent voxel grid, and then we are denoising it to get the new representation that is then called VT there in the end. And then we take, for the second part, then when we have our denoised voxel grid, this is at 0 in the end by the diffusion model, we take our learned decoder that decodes now the latent representation into this nice point cloud here. And so in the end, we can take this latent representation, sample it, and then turn this into a scene via the diffusion model, and then take the latent decoder to basically turn it into a full point cloud. And we can now do two interesting things with it. We can do the unconditional scene generation. It looks then something like this. It's completely, it looks like Kitty, but is not Kitty in the end. Or was never there annotated in Kitty. We can generate novel scenes, but more interestingly, we can also generate new scenarios and a lot of scenarios for this. So this is really just a completely not a non-existing thing, but we can also, that's now the cool thing about it, we can also condition it. And since it learned something about the world via this process, via this variational autoencoder and the diffusion process, we can apply it to novel data. And this is really a cool thing because this, as you see, the buildings are much higher because we are now using not only the Kitty sensor, which was a Velodyne that has a narrow field of view, but we are using now the Auster sensor, which has a larger field of view and also more beams. So these are 128 beams, and our original model was trained with 64 beams. And we can now take the scene and just apply our approach and get a quite convincing representation out, also semantically. And I find this very cool because this was never intended by us, that we can take it to novel data and then generate something like this scene out of this. To make it even more interesting, we can now concatenate all the scenes together and generate basically a new Kitty world, so to say. And again, the video should play. Sorry. Okay. And we can just stitch them together. So we generated just scenes and we just stitched them together. So we have now here a new world where you see cars are generated in a sensible place. We have some street geometry. But of course, as I said, not only ChatGPT does sometimes some errors, but also our approach, when you see then here that it's going around the corner, then you have maybe something in the real world not happening, that the streets are maybe not fitting together. But this is what we can do then with this. And the thing is now we have this then scene, we have this then scene geometry with labels attached to it. And the thing that I said, we want to use this also for training. Therefore, we can now generate a scene and then simulate with the scene a semantic LiDAR scan. And there we are just using the sensor geometry so that we have the 64 beams or 128 beams that we know how to ray trace, and then we can generate the simulated LiDAR scans. And to really try it out, we tried out different scene generation approaches. So these are all contemporary or different approaches from last year or the year before that can generate the scenes at a specific resolution. And then we took the scenes and trained a neural network with it. And then you see on the right side, so a semantic segmentation network with it. And on the right side, oh no, sorry, that was the other slide. In this slide, the evaluation is like, the idea is that we can take a semantic segmentation network and apply it to the generated scenes. And the idea is when our scenes look more real or realistic, then they should have a good performance in terms of the mean intersection over union, so on the performance of the semantic segmentation. And the closer it looks to the real scenes, the higher the MIOU should be in the end. So therefore, this should verify that it looks closer to real scenes. We have also this distribution metrics that were also more convincing, but I think that that's actually what we are interested in, that our scenes look also to the neural network realistic in the end. The other thing that we can do is now that we can do the scene simulation, that we generate first the scene and sample the point cloud from it. And then you can see here that we now mixed real and synthetic data together for the training. I should do it here. We have here now the mix of real and synthetic data, because what we figured out that when we are just using, using most of it just synthetic data, it doesn't work so well. So therefore the MIOU is dropping compared to the performance that we have when we are just training on normal data. Therefore, what we figured out is that you have to use basically some synthetic but some real data. So it's not until now at the phase that we can live without annotating any data, but we can actually reduce the amount that we can annotate data. And when we are not doing this just for the simulated LiDAR scans, but also for the real dense point clouds, then you can see that the gain in performance compared to not using any simulated data at all is then also much more drastic. So but we are currently also working on this to make this even more, or make this even better. And also compared to other scene generation approaches like this X-Cube, we get also quite significant improvements there. So with this, I am already at the end of my second part. So I showed you now an approach that can basically turn a lot of annotated training data into a model with which we can then sample new examples of semantic scenes that we can then also employ for learning a semantic interpretation model. This diffusion approach on this latent space leads to more realistic scene generation results, and as you have seen, or I hopefully convinced you that it reached competitive gene generation results in the end. The disclaimer, this was actually not my work. I was only in the supervision there, or co-supervision with Cyril involved, nudging our student Lucas Nunes, who's basically also now finishing just this week his PhD. So he's handing in his PhD thesis, and therefore he's also looking for postdoc positions. So therefore, just to let you know, so he's our scene generation guy. So with this, I'm at the end, and thank you for your attention.
Thank you for the great talk. Guess there are a couple of questions here.
Oui.
Yeah.
Hello. Thank you, Professor, for your great presentation. And regarding the first part of your talk, I'm wondering, is there any problem with dynamic objects when you? Yeah.
Okay, that's something I wanted not to tell. That we actually use the semantic annotations that we have for Kitty to remove the dynamics. For now, it's just working with static scenes. So we train only on static scenes, because in semantic Kitty we have annotated all the dynamics. We are removing this because this, of course, when you aggregate the scans, you have these trails. But another student was working on an approach to do reconstruction with dynamics. Probably that's future work. So for now, it's dynamics play no role.
Okay, but regarding the input of the first approach, we need to remove the dynamics, the ghost, right? The LiDAR ghost on the thread before we input those data to train, right?
Yeah, exactly. This would then you would have it in, so we remove it. Yep. So we aggregate the data, we've removed it. But when it would be in there, we would of course have this multiple multiple scans, this goes. Yeah, exactly.
Okay, okay, thank you.
Yeah, so the approach cannot handle this. So it will learn that basically this goes there, and this looks not so nice. We tried it, of course, and therefore removed it, basically.
Okay, and yeah, thank you. And is it possible to reuse this approach in indoor scenario?
Technically, yes. So there maybe you can do more because it's just smaller. Because here the biggest problem is that you have this large scene scale. So we are talking about point clouds of something like 50 meter range, 50 by 50.
Yeah.
When you're going maybe in this room, then you can maybe make even the resolution smaller, because this is all based on a voxelized representation. So it's taking the point clouds first, doing some reduction to a voxel representation, and then we are using sparse voxel convolutions on top of it, and then we are turning it back into a point cloud from these voxels. So therefore, when you're going indoors, you probably can make even the resolution much finer.
But I'm thinking about another challenge maybe, because in those scenarios there are a lot of glasses or transparent objects, right? So the distribution of this kind of point cloud is different from the point cloud from outdoor scenario.
Yeah.
Right? So so is there any potential way to deal with this case?
For now, we are just ignoring this, because it happens, of course, also in the outside, because you have glass surfaces, you have, just field measurements and so on. So therefore, currently it's in the data. You will also see it when you look basically below the ground, and you will have also some outliers, but currently we are not taking care of this. So probably an approach for dealing with this would be me using some visual data, because it's much easier to detect that there's a mirror when you have some vision input, for instance.
Okay. And following your comment on this, I have another question regarding the second part of your talk. So I say that the generated data is all in LiDAR point cloud, right? But is it possible to generate the paired video or image?
Technically, from the diffusion approach, is exactly the same that we do also for images. So therefore, you could pair it also to generate images on top of it. And there's also, I think, approaches that turn LiDAR scans into images. And
you mean just translated LiDAR point cloud to images?
I saw some papers on CVPR that actually do this. So they have paired data, train a generative approach that it just can take a LiDAR point cloud, and then they generate a visual representation of this. But of course, it has then all the things that you have in your training data. So it will then generate always something like kitty worlds or something like this.
Okay. Thank you so much. Okay.
There's another question over there.
Thanks, a great talk. And could you please go back 2 slides for the results? Yes, here, So here, I'm not sure if I interpret this graph very well, but if you look at the 50-50%, here it means that you use the 50% of synthetic data and 50% of real data, then you can even achieve the better results than the model with 100% of the real labels. And the number of the samples are the same or not? Number of chains?
I am not sure. I don't remember. I would have to look in the paper.
Yeah, because here you present the percentage of the real and synthetic. So suppose that if you use the let's say 10,000 of the real labels, and then but with the 50% of case you use the 1,000 synthetic data, 1,000 real data, then the performance of the model is better than the model with the full. That's.
I guess this is really like because it's converging to. it's converging to the performance of using only real data.
Yeah.
So I guess this is adding 10% of synthetic data, adding 50%.
Okay, okay. Adding
So
more.
I think it's additional. And what you can see is that when the synthetic data gets basically too much, it's basically not possible to take any more this correct information. But as I said, I'm not to, or I don't remember how it exactly was, but for me it would make sense that when you take only real data, that it converges to the performance. So the dashed line is basically performance of just using real data.
Yeah, and then you add, for instance, a
we
few
add
additional synthetic data.
10%, yeah.
Yeah, and it's increasing, I can understand, but if you, let's say, if the synthetic data dominates the whole data set, then the performance decreases a lot, right?
Yeah. So that's the idea that you should get.
Okay,
Not too much synthetic, you need some real data.
Okay.
But
The kind
I
of
think
balance, trade-off between.
I think that's also the usual thing that also other people for image generation found out, that you need some real data, because usually all diffusion approaches, also ours, are basically trained for some objective that is maybe not realness in the end, but appealingness or something like this. So that it looks close to what a sensor would produce, but it cannot perfectly reconstruct what a sensor would do in the end.
Okay,
so
I
therefore for images it's the same. So there was some experiments with Lion, and then they're taking different splits. There's the paper promise of image generation. Yeah, can look it up.
Okay.
So
Thank you so much.
I do have one question, if I may. So if you think about potential downstream tasks, like let's assume we are doing object recognition, or you could even think about SLAM also. SLAM is probabilistic, but let's talk about object detection. So does this actually help with object detection, or, normally you could also think about that this object detection approach does this intrinsically, right? So in a kind of like an end-to-end fashion. Or what is your observation there, right?
yes, so our whole idea is that we maybe can generate more scenes that are maybe showing it from different viewpoints, for instance. And with this, the hope is that it gets more generalized. Because usually you just apply some data augmentation, so you try to modify the data, and here it's really like that we try to generate new scenarios, and then we hoped to make it more generalizable or robust even in the end.
And when you think about SLAM, right, you would actually also be interested in uncertainties there, right? Because when you want to do data association, also, right?
All these approaches have no uncertainty assigned, and it's also, I think, also a big problem how to pair all this deep learning with our probabilistic approaches that have still some right to be there, to link them together. So we need some uncertainty estimate in the end. Yes, that's correct.
Great. Any final question? This brings us to the end of the scientific presentations here. Thanks a lot. The plan for now is to clean up the stage, do another group photo, then set up the chairs for the podium discussion, and then we will head for lunch. Great. So give them a few minutes, then we will take another group picture because we have different people here today.
missing one person.
Yusuf?
Where's
War
Yusuf?
eben da, nicht, oder? Vielleicht ist er kurz zur Toilette
Maybe
gegangen.
gone to the bathroom.
You snooze, you lose. No?
Wow, das ist ein schöner Song.
Ja, das ist gut.
Alexander Martin ist gestern da, oder?
War gestern der Workshop am genau. Das war echt cool. Wann bist du angekommen?
21:30 Uhr oder 21 Uhr.
Waren wir noch da?
Achso, okay. Die andere Rezeption noch nicht gesagt. Okay, sonst wäre ich ja noch gekommen. Ich war auch ziemlich tot.
He said hello and then he runs off.
Ich hatte ja gestern 2
Maybe he's so nervous he had to go to the bathroom.
Nee, einen auf der Konferenz und dann noch IHK virtuell anschauen. Achso, der Yusuf ist hier. Oh, der war auch hier.
Ja, da kommt ein Foto.
Der war doch gerade hier. Doch,
Eben
hallo.
gerade.
Haben sie gefunden? Achso, okay.
Bravo!
We were worried. I just
Okay,
But you washed your hands, right?
okay. Shall we make a start? Yeah. It's my great pleasure to moderate the panel. So the theme of the panel is on the challenges of embodied intelligence. So we have 4 panel members. I'm Shan Luo. I'm professor of robotics and AI at King's College London. So it's my great pleasure to moderate the panel. And shall we have a quick round of self-introduction? Yeah, so we can start.
Josef Grabowska, Professor of Machine Learning at the University of Technology in Nuremberg.
Yeah, Gitta Coutunyok, Professor for Mathematical Foundations of AI at LMU Munich. I also serve as the director for the Konrad Zuse School of Excellence in Reliable AI between LMU and TUM, and I'm also the spokesperson for the AI Hub at LMU.
I'm Wolfram Burgert. I'm heading the research team for robotics and AI here at the University of Technology Nuremberg, and I'm also department chair and trying to set up this university.
I'm Oliver Brock from Berlin, and I'm a roboticist.
Okay, great. As well, in the past 2 days, we have seen great talks in the workshop, and we have got a lot of brainstorming. And this is the end of the workshop, so we would like to look at the challenges forward in the future. So the very first question for the panelists is, what do you see as the core challenges currently limiting progress in embodied AI?
Everything.
Everything.
I don't think we know what we're doing, and which is not surprising, right? Robotics as a discipline is 50, 60 years old. I think we're trying to be like physics, which might not be the best approach for us because it's very narrow, right? We're trying to model everything very precisely. Well, this was true for a while. Now we shifted to completely not modeling anything explicitly. So I'm not sure if either of these extremes are the right thing to do. But yeah, I think we don't know much about embodied AI or intelligence in general. So everything is a challenge. And I think the biggest challenge, to give some answer, is in our own mind, right? I think that we're very locked into very mature sciences, trying to be like them rather than following our own intuition.
Yeah, I think that's a very big challenge. Yeah.
Yeah, I think 2 challenges I mentioned in my talk, reliability and sustainability, which already at the level of, let's say, cognitive AI is a challenge. But in general, I mean, coming, let's say, from the outside a bit to robotics, what I always would wish for is, I mean, I think there are a lot of great developments in various labs worldwide. You see these amazing videos, but it's very hard to compare. Yeah, so is this robot from this lab better than a robot from another lab? So to derive somehow quality standards, and if you compare this area with telecommunication, I mean, there you have the G levels. Yeah, so people know where they work towards. They have a fair, let's say, comparison system. What is better than something else? So what I would always wish for, and which to my mind might also then, I mean, bring robotics further, would be also like quality metrics, according to which you can then compare robots in a more fair and objective way, and so that you can then see that maybe some robots are better than the other. I mean, one very small measure could be, I don't know, energy, reliability, and so on, and maybe one can draw also from other areas to develop measures, quality measures, maybe standardizations according to that.
I think that the main challenge, in my perspective, is that optimal control in the real world is a very complex problem. And just to give perhaps an illustration, a honeybee, a small insect, has 1 million neurons and approximately 1,000 synaptic connections for each neuron. That amounts to approximately 1 trillion parameters in the cognitive system. That is equivalent to a GPT-4 level transformers. We currently can pack this intelligence on perhaps a server with 8 GPU cards and run this transformer there. And that is the equivalent of the cognitive system that a bee has in a 1 centimeter square. So we need better infrastructure and better way to pack intelligence into tight volumes. And that is a challenge that we have for the future. And if we consider the simplicity of the actions that a honeybee conducts, which doesn't, for instance, have to interact with vision language instructions as we would expect other robots to do, this shows clearly that optimal control is a very complex problem that will be of a high priority for the next decades.
Go ahead.
Yeah, I mean, I feel like I want to respond to that. I mean, obviously, control is a difficult thing. I don't want to question this. But these comparisons of how many parameters and so on, I don't think that works. You know, Ray Kurzweil was predicting the singularity for, I think, this year, right? Maybe? And obviously it hasn't happened, right? He said, oh, you know, the number of flops done in the brain is this number, and now we'll have computers that do this number of flops. So therefore, it's not about how many neurons or connections. It's what kind of computation do we do, right? And this is the question. In some sense, how are the neurons connected? What's the algorithm actually running? And only when you have comparable computation, but also the comparable algorithm, can you actually compare those systems. So I think, yeah, that's. I think we have to be very careful with these analogies. They tend to not work out.
So I agree with you. I think that an advance is needed on both fronts, but if you have a limitation on the compute, then novelties in algorithms, they tend to be limited too. And there is a famous paradigm that any stupid algorithm that can scale with compute will in the long run outsmart all clever and complex algorithms that are not scalable with compute.
But this is in principle, right? So just like in principle, we have solved intelligence because I forgot the guy's name, but he wrote down like a 3-line formula, an optimization problem, right? So we're not in the in principle business because intelligence is not solving things in principle, it's actually solving them with resource constraints. So the thing that we're trying to find is a way to solve all these problems given reasonable constraints. You know, I mean, PowerPoint is Turing complete, right? You can program anything that you can compute in PowerPoint. That doesn't mean that PowerPoint, will eventually be an AI, right? Nobody would ever try to do that. So, yeah, I think, that's what I wanted to say.
But maybe you can do your presentations then, right? From scratch. PowerPoint.
Yes. I thought you said representations.
No,
and that would have been a different meaning. Yeah.
I agree with many of the arguments that you raised, especially when we look into several applications of embodied AI, which is an umbrella term for different problem definitions. But at the heart, the current usage, for instance, of vision language models in robotics to solve different use cases is very human-centric, is how we perceive the world, using data sets of realistic images. But for many applications, just maybe to stick with the analogy of the honeybee, it doesn't see the world in the same resolution. It doesn't capture the same level of perception. So the representation learning of the world for a particular task is not necessarily what humans perceive. So we need to adapt the cognitive systems, the models of different applications to the level of details that is needed for the task. So we need better representation learning on a visual level in order to adapt, as you said, to have a better, more clever way to represent data for that application.
I completely agree with that. I just don't think that that the models that we have today are actually doing that, right? And in some sense, we've given up the algorithmic side, and we're saying, you know, if we just use data, a neural network will magically then, well, maybe not magically, backpropagation, will then encode the algorithm somehow, right? And I really wonder if this is circular reasoning, right? If we believe John Mitchell, who said that you need an inductive bias to generalize, right? Then if you say this inductive bias is going to come from data, there's a break in the loop, right? I mean, in order to come up with the inductive bias from data, you already need an inductive bias. To come up with that, you can do it from data, but then you need some other inductive bias. So maybe the start is the right inductive bias and everything follows. We've given up that route, and now we're just trying to solve everything from data. And like I said, I think maybe that is a circular reasoning. You know, we're trying to pull ourselves by the hair out of the swamp. That's a German story.
Yeah.
No, go ahead.
Okay, yeah, we have mentioned about data, we have mentioned neurons and also algorithms. But for embodied AI, so compared to software AI, we see, so the key difference is the hardware. So that's how we embody the robot to have the intelligence. So in that sense, how do you find the challenges in designing robot hardware or hardware for intelligence in general? And also from there, how can we co-design hardware and software altogether for embodied AI?
I mean, I mentioned this yesterday a little bit in my question to, I think, to Tamim. I think that right now we are in this phase where we are actually playing around with the generative AI tools, and we are like enjoying how far we can get with all of this, right? So how far it takes us and which functions we can realize. But in these talks yesterday and today as well, we also saw substantial limitations there, like this lack of introspection, for example, like this inability to reason about its own success and so on and so forth, right? This is something that is a real limitation, which also comes from the fact that the systems that we are seeing right now, they don't act in the real world. Their real world is the internet, right? They consume images and they consume text. They maybe get some feedback from users, but this is basically it. And what we are really lacking is that being able to do this with a real physical agent acting in the real world. And that basically means that we need to add further modalities. And that brings us to this question of new hardware, right? So, I mean, I think humanoids are great, simply because they maybe allow us to perceive the world in the very same way as we do. So, but that requires that we need to have hands that can actually have the sense of touch, that we can actually feel the world, that we can also like have the similar forces, so that we basically, in the end, hopefully speak the same languages the same language as these robots. And this is why I think this hardware development or movement towards humanoids is so important right now, and maybe pathway to accelerate our development of these intelligent machines. And this is something that is, from my perspective, a little bit underestimated. So when you look at the humanoids that you see right now, they have very, very simplistic hands, very, very little tactile perception, not in the variety that we have. I know that brings problems, right? That's why I asked Frank about communication on platforms. I mean, a tactile sensor is almost a camera, right? And how many cameras can you have on a robot? And like how many cables would you need in order to have like connect every tactile, like binary tactile information, or let's call it a byte or so that you would get. You will need millions of those. Right? So communication on these platforms is a real challenge, and I think for building truly embedded robots, we need to have this information, and then we can also maybe build finally a robot foundation model. But for that we also need to have the specific hardware, and we are far away from that.
Yeah, I think that the term embodiment is an example for what I mentioned earlier, that we have kind of fences in our head that limit us. The term embodiment came from the realization that the kind of computer systems that we build, as you just said, right, they interact not with the real world, but with some virtual, very clear world. And somehow the term embodied was used to designate that something was different about biological systems. And that has to do with the body, obviously, because in the body we live and we can interact with the world. But I think the term embodiment is confusing because it means actually, it includes many other things. It means kind of that you're situated in the real world, that you're interacting with the real world. But I think most importantly, it means that we can use our body to perform computation. Right? If you do something in a CPU or in a GPU, it's kind of all digital computation. And we know that if you want to factorize a large number, you shouldn't use digital computation, you should use quantum once that becomes available, right? So every computational paradigm is particularly well suited for a particular type of problem. Quantum computing for factorization, CPU maybe for kind of general function computation. And our body is very well designed to perform computations when interacting with the real world. So we use our neural computation together with our mechanical computation that's encoded in the way our bones are structured, muscles and ligaments and our tissue. Everything is designed to perform computation effectively. And so I think embodiment, to me, the most important aspect is that in order to achieve intelligence, you need to combine multiple computational paradigms, at least digital/neural computation and mechanical computation, because that enables interacting with the world.
Yeah, I think that you raise a very good point. So embodied intelligence is not only neural intelligence, but also the mechanical intelligence embodied in the physical bodies. Yeah. So we can also look at the natural system, like, so different organisms may have different morphologies, different structures. Like in nature, the fish can swim very well in water, so they have very different morphology compared to humans. So they have their own intelligence in their body. So how we can leverage such physical intelligence to power embodied AI could be a very interesting direction.
I think that's really the core question of robotics that we haven't gotten to yet. Right? It's the question of co-design. The behavior of a system is the result from the control system and the body. And in order to get the best behavior that we want to have, we need to design the two together. We cannot, this is what we've been doing in robotics, because we come from a scientific tradition of divide and conquer. We've divided into control and into building the mechanism. People have done that separately, not in robotics. In robotics, everything is connected, right? And so we need to understand, and we have zero understanding of that right now, how do we co-design something? We have ideas on how to design a good robot There are some, design rules. We know how to make good controllers. We have a bunch of control approaches that are very powerful, and we can prove nice properties about them. But when you do the two together, we really don't know how this interaction works. And I think that's what nature has figured out through evolution and kind of, guided random search, that these two things evolve to an optimal division of problem solution between the body and the brain.
Yeah. So I completely agree. I think co-design is extremely important, and maybe this also relates to what I said before. I mean, on the, let's say, software side, that there also the software and the hardware need to be co-designed together. But I think in robotic, one could go even one step further and say what we need is also an AI system which aids in this co-design, and then maybe already made suggestions concerning what could be a good further embodiment. So like having an AI engine to guide the co-design, certainly then, I mean, in the beginning also with a human looking on top of it, but then, I mean, basically guiding it itself.
Concerning your point regarding the interaction between software and hardware, I think that we need to invest more efforts into neural architecture search techniques to find optimal architectures for specific devices. It could be that the transformers architecture is not a winning solution for every instance. And in that case, we need to search for optimal architectures in multiple objectives. We need low latency, we need low energy and low memory consumption, so the 3L objectives. And we need to find architectures at the Pareto front across those objectives. The second software level innovation that is needed is how to have memory and power efficient adaptation of those models into out-of-distribution scenarios. So we need incremental, continuous learning of those agents in a way that is efficient. So in addition to the hardware, I think the architecture search and the online or incremental learning, and that links very well to what Oliver mentioned, that we still need algorithms, we still need clever learning paradigms in order to make progress.
Yeah, that's great. So this comes to our next question. Actually, we have already mentioned some of the aspect of the question. So in different fields, we have metrics to evaluate the success of algorithms, for example. So we have mentioned the quality metric for image comparisons, and also in machine learning, there are many standardized metrics to evaluate the success of algorithms. But for embodied AI, it's very challenging to define like universal metrics to measure the success of embodied AI. So in your view, how do we define success for embodied AI? Is it human level, dexterity, generalization across tasks for like auto-distribution, performance, or others?
Yeah, I think that's a very difficult question, but I think without that, I mean, we cannot make, let's say, real systematic progress. Certainly, I mean, if you think of how humans learn and how humans are educated in different professions, I mean, there are also certain, let's say, levels they need to reach. So one could borrow from that in a certain sense. I mean, then on the cognitive side, I mean, the whole area of education, neuroscience also already has in place some of those measures. And then certainly, I mean, one need benchmarks, like things, for instance, of imaging. There you had this huge range of images. Everybody knows about Lina and Monkey and so on and so on. Yeah, but now for robotics, it's certainly much more difficult, but one could have really specific, let's say, benchmarks environments where robots are then tested in the same environment, and then one could fairly compare them. So this will be a huge effort in that respect. But again, I mean, looking at what are already in place, let's say from human training in a certain sense, and then complement that also with real benchmark environments.
Sorry for the interruption. So actually, that reminds me the benchmark of the pathway to the AGI. someone called AGI, artificial general intelligence. So in this year, I thought the statement said that okay, if you asked the people 3 years ago whether the current performance of the AI is the AGI, they would say no. They would say yes. Yeah? But you know, the benchmark, it's always evolving. Right? So in the beginning, they had, well, now we see simple benchmarks, but with the involvement of the AI capability, then they make the more and more complicated benchmarks. So from this perspective, I was thinking whether embodied AI can follow the similar way. We should not establish the benchmark in a very complex way, but in a basic intelligence, let's say, with benchmark with the simple intelligence, and everybody set up this benchmark and then test the performance. And if most of them the embodied AI achieve this benchmark, then we can the society or the community can set up a little bit more complicated targets. Well, that remind me the pathway of the AGI.
I mean, while I agree with all of these wishes to have something like a benchmark there, we also need to be aware that it's really complicated to do something like this. And on top of this, it always comes with the risk of overfitting. Right? At some point in time, right, people start like getting too close to the specifica of that benchmark. For me, the best benchmark is the real world, and I mean, this is what in self-driving car is being done, right? So you can actually look at how long cars can drive autonomously in the real world. Like, what's the mean time between failure, right? This is something that we and there we also don't limit. Like, we do not have test tracks where cars drive. We put them into the real world and measure how many kilometers they run without a failure. This might be a relatively good benchmark for embodied robots as well, right? So if we really think about this, then put them into the real world and see how long it takes until they break or until they break something or fail. Yeah, that would be my hope, that we can have this as a benchmark in the near future. And I mean, you really think about, like, we are producing like thousands of humanoid robots per year, right? And we are hopefully able to buy them in the near future, right? Put them into our homes, and let's see as to whether they can do useful tasks, and as to whether people buy them because they love them taking the things that they don't want to do, or doing the things that they don't want to do. Right? So this would be the ideal benchmark from my side. And whenever you specify something, you come with this risk of overfitting. Right?
Yeah, I think that benchmarks are interesting, and I think we need to completely rethink them in the context of embodied intelligence. So a benchmark tests a specific behavior, making strong assumptions about what it is that you're testing. So if you're testing how many multiplications can you do, it doesn't make sense to compare a 5-year-old child with a CPU, right? So in defining the benchmark, you're assuming that everything is a CPU that you're comparing, and then the benchmark makes sense, right? If you don't know what it is that you're testing, then you cannot define a benchmark. And this is true for humans, right? If you take a driver's test, I drive for 10 minutes, right? And then the driving instructor says, okay, now I'm giving you this piece of paper and you can drive for the rest of your life among real people, right? And that is because there are huge assumptions about me as a human. The instructor says, well, it doesn't matter if it snows tomorrow, Oliver will be able to generalize, right? So we're making strong assumptions about this benchmark of passing a driver's test. So I think as we're developing these agents that we want to benchmark eventually, we need something else than a benchmark. I think we shouldn't try to benchmark the agent's behavior. We need to benchmark, then I wouldn't call it benchmark, but we need to expose things that the method, the mechanism that computes the behavior does. So, for example, we all talk about generalization. I think generalization is interesting because it might not exist, right? I might actually not generalize. It's just that if I see a problem and another problem and I apply the same method, you can say that I generalized between the two, but with some features, they were the same to me, right? So I didn't have to generalize because I had a representation in which these two problems already were the same. So maybe we need to try to characterize for an agent that knows how to do one task, what is the space of situations that looks the same? And we can maybe characterize that and quantify that. And the bigger that space is, the better the agent is. Right? So that's not a benchmark, that's a characterization. It's more like horsepower, right? It's something inside the engine. But I think this will give us a gradient, right? Because we can make that space bigger and bigger and bigger, and our agent will become more and more general. I think that's a gradient that would be helpful for us to develop more interesting systems on our way to AGI, maybe.
Yeah, I completely agree with that. But I mean, let's say, looking at this core ability of agents to generalize or to transfer learning. For a human, you believe that humans can do that because they can do that already for, I don't know, thousands of years. But with an agent, it's not that clear. So, I mean, to test this ability of transfer learning, I mean, this could be also with some benchmarks, so that you test this core ability to transfer. And then, I mean, Wolfram, what you said, I mean, putting the robots in the real world, I also completely agree. But the real world also have different places, yeah? And so if you have to take a driver's test, I mean, then you drive on the Autobahn, you drive in a little city, you drive at night, so you have different scenarios during which you put yourself or then, I mean, someone else. So in that sense, I mean, even if you go to the real world, you need there different, very specific scenarios to test whether all these aspects of a real world are basically handled correctly. Or maybe you meant that, maybe I misunderstood.
I mean, I like this this idea of these driver tests, right? So, but this comes with the assumption that, like, when the person passes this test, we know that it is kind of behaving correctly in later on for the rest of the life, which is crazy as well. Right? But I mean, this is something that we don't have from these agents that we built these days, right? We have no clue what the system will say, like for a different prompt, right? It's hard for us to predict as to whether this is meaningful. And we saw really meaningless prompts or outputs during this conference here, right? So that's one of the problems, and that's why it's so important to have these introspection capabilities and maybe also like this interpretability, right? So because we don't exactly know what these systems are going to do. This is why people like to see benchmarks, but what we would actually like to have is systems that are so reliable that we can test them and basically say, based on this test, right, it's going to pass and can act in the real world and walk around in Nuremberg. And I think this is, the big challenge that we are facing. Like, how can we actually test these systems in a proper way? I mean, in academia, I completely agree. Like, yes, we need to make progress and document progress. We create a benchmark, and people are happy to become first on the leaderboard for 2 weeks, something like this. And doing this 4 times gives a PhD, something like this. But I mean, if you really think about where we want to be, then we would need to have this. We need to have this ability to have, like, to understand what this agent is doing, and this trust that we develop in this agent by interacting with it.
Okay. Yeah.
I think that for a particular agent, it is important to have benchmarks on the operational objectives. To perform a task fast, etc. We also have constraints, and the constraints regard safety, they regard potentially regulations and laws, but there is a hidden dimension that those benchmarks should fulfill. They should fulfill our principles. And principles are a little bit more difficult to benchmark, because not certainly principles equal regulations or constraints. And that, I think, in the long run, since our colleague from the audience mentioned AGI, we need to better better be able to formalize our principles and how we can materialize them into concrete ways of measuring whether those particular agents fulfill our principles, not just the operational benchmarks.
Yep, that's great. We have taken autonomous driving as an example a lot. So in the very last talk we got this morning, so for autonomous driving, we have different levels of autonomy. So we have arrived at level 6 autonomy for autonomous driving. So we may have such levels for embodied AI as well. So we can set up these levels instead of like a benchmark, so we can progress the technology for embodied AI. A relevant question, so many of these embodied AI developments rely on simulation. So we may develop algorithms or hardware, even hardware in simulation before we deploy in the real life. So in your view, how do you see the role of simulation in the landscape of embodied AI, and how can we bridge the same to real gap so that policy trend in simulation can be transferred more robustly to the real world?
You have stuff in your paper about that. Right? No?
About simulations?
Yeah, no?
Simulations would be not me, but I mean, I think in general, I mean, I can say something about simulations in general. I mean,
Definitely to put you on the spot.
okay, you know, no, I mean, I think simulations, I mean, this is extremely important. If you would have a simulation environment, I mean, then certainly, I mean, the robots could be trained in this simulation environments for different tasks. It would be extremely more effective than, I mean, let's say, training them in the real world. I mean, it would be like a two-stage progress like you train also now foundation models. You could train it first in simulations, and then you could train it otherwards in the real world. But I mean, in general, I mean, simulations could be then also used for a benchmark. So, yeah, but I think that's an extremely important direction.
I see it as well, but I'm also super skeptical about simulations, simply because when I worked in the self-driving car business in a research company, I realized that building a good simulator is actually extremely hard. And so if you take this to the extreme, like if you want to have a perfect simulator, right, then you solve the problem. Look, for example, at self-driving cars. Right? So when I worked with TRI, we had a visitor, which is a company that builds graphic cards, and they do simulations, in fact, in order to have people buy graphic cards. And they came up with or showed us their simulation. It looked super realistic, but the agents were actually really dumb. Right? They were basically, the cars were like constant velocity models. Right? This is not what the real world is. You know? So, and now imagine you want to have a truly intelligent agent in your car simulator. Right? So in order to do this, you need to have kind of like human-like driving. Right? You need to have cars that behave like humans. And if you have a car that behaves like a human, you solve the self-driving car problem. Right? Because, I mean, you want to do like, you want to have the same perceptions, you want to have like, simulating LiDAR is a little bit easier, but simulating vision is extremely hard. And then simulating other agents is hard, right? So, for example, if you're able to simulate a dog, right, you would be able to actually make perfect predictions what this dog is going to do. So you would have a world model for a dog, right, which is, or take a pedestrian. You would have a world model for a pedestrian, right, which is basically like implementing its intelligence. Right? So building a perfect simulator, like, yes, go for it, but you then solve the problem at the very same time. Maybe it's easier because you don't need to go into the physical world, but I doubt that we will be able to do this, right? To basically, and of course, when we solve the problem, then we have a world model for everything. We have a perfect simulation. I do not know what the better approach is, like going through simulation or going through the real world. I think the real world is probably easier for us because it comes for free.
I totally agree with everything you said, and I really think the real world is easier than trying to get a simulation and then solving it in simulation. And I think there used to be a time in robotics which doesn't mean that it's the right thing, but there used to be a time in robotics when nobody questioned this, where everybody thought, if you do it in the real world, that's much better than if you do it in simulation. And my feeling is that there was a shift in thinking about this as a consequence of the need of having lots of data imposed by the gold rush that was triggered by deep learning, right? As it always happens with the gold rush, people become, I'm not going to say irrational, but people change their priorities, let me say it this way. And so right now, I feel we're spending time building simulators, we're spending time building systems that gather data, we're trying to fix the holes in our method, right? There's a whole culture, a whole industry in support of everything that is deep learning. Fixing the problems, providing the data, building the nuclear power plants. I mean, it's everywhere, but nobody questions whether maybe deep learning is not the right method. And I'm not saying it's not, but I'm saying we should, if we're reasonable, at least ask that question. Because we're about to change the surface of our planet in service to this method. We're changing our education. Like I said, we're changing our energy infrastructure. We're changing economics in service to this one idea. And I don't know, to me it would seem reasonable that if we do that, we at least ask 2 or 3 questions about it. And so I think that this real deep belief in deep learning has caused us to change our view on simulation. And we now like it much better than we used to.
We always do this. We also love smartphones. That's why we run around with smartphones. Change the world as well, Oliver.
Well, I'm not against changing the world. But we have to agree that there are some changes for the better and some changes for the worse. There are no changes that are all good and all bad. I also agree with that. But I think as a species, we should try to prefer changes to the world that make things better.
If I might disagree with that statement.
Please, let's go.
I think that the community of researchers criticized for almost 1.5 decades deep learning in favor of other approaches, more intelligent exemplar-based techniques such as support vector machines. So there was a gap from the 90s until the late 2010 where deep learning was heavily criticized as a joke, a biologically inspired method that we try to copy models in a kitsch way. And deep learning actually proved its worthiness the hard way, not the easy way. So we're not being fooled by deep learning. Deep learning convinced us that it works.
I think this is an indication that you've been fooled. I mean, how can you say that, right? I mean, we don't know if it's going to work, right? And I think if you really think about it, you will agree. It has done amazing things. It's a tool that's here to stay. There's no question about it. But it's not the solution as we're seeing, right? It requires a lot of work, billions. I mean, for the first time in the history of our planet, we have picked one idea and we're pouring billions into it. I mean, literally billions, right? Every year. This has never happened before. With no idea on this planet has there been such a monoculture.
It happened with the diesel engine.
With what?
It happened with the diesel engine.
No, this took a long time. It took centuries, it took decades before there were more than 1,000 cars, right? I mean, it took a long time. It happened over a much slower time. And the investments, I mean, come on, it was 5 people in some shack that did it. It wasn't 10 of the biggest companies of the world, you know, hiring people for $150 million a year. I mean, come on, it's completely insane. And I think you will have to agree, right? I mean, what's going on is not sane.
It seems I don't have another option.
Yeah, exactly.
Yeah, and I also tend to agree, because now, I mean, we really believe in this one idea and also throw a lot of knowledge overboard. Yeah? I mean, when you talk to students, they say, why should we learn physics? Why should we learn chemistry? We just have the data. And I think this is a very dangerous development. So in that sense, it's almost like a God which we created there.
I agree.
I mean, I don't see it all negative, yeah, but I mean, I think one need to be conscious about it and really evaluate what we need to also keep as a knowledge and what a good, let's say, handling of this new God is.
Yeah, let's change it to.
There was somebody who.
Thank you. May I ask a question? So the application scenario of the embodied AI mostly is in the home or in the campus or in the manufacturer. The computation source is always in the data center, and we through the wire or fiber communication and wireless like Wi-Fi or 6G and to our robot. And we want to ask what's the challenge of the communication network, and how can we through the communication to help the embodied AI development? Thank you.
I mean, Frank talked about this earlier today as well, right? I mean, of course, if we stick with the current paradigm, then Gita also showed these graphs, right? Then it's going to go crazy, right? What we need in terms of compute, network, infrastructure, and energy. Right? It's, I think this is not sustainable, and I mean that will also probably introduce some pressure onto research to go to investigate different directions. Right? When we reach this limit that only a few companies can do or calculate these models simply because they only have access to a nuclear plant, right? And then yes, then this probably will somehow die out, and we as researchers need to figure out new ways. And then also if we lack the diversity and the competition, right, then this will also become problematic because it's not going to be open anymore, right? You never know what's going to be in these models and so on and so forth. So there is a risk that this is not sustainable, right, that this entire process. But I'm not afraid about this, right, because I think that we, maybe by other measures, right, we'll get beyond that, right? So, I mean, it refers to computing architectures, right? Nobody knows as to whether backpropagation is actually great, but it's probably also the problem behind all of this, right? Because we are stuck with this algorithm. And we probably need a different algorithm to have better computers, better machines in the future. Right? So this entire problem of incremental learning, Josef mentioned that, this is all due to this algorithm because we do not know how to properly do this. But this will be one of the key challenges for the future. We need to get rid of this, and we need to solve this problem of being able to do incremental learning in order to actually solve the energy problem. And there will be revolutions in the future. Which ones that are, I don't know. This is why I also partly agree with Oliver. I also think that this is a great time, right? These systems are doing amazing jobs, apart from some things that they can't do at all, which we also saw. But I mean, we need to solve these things in the future, and these are the challenges. And I'm optimistic that we'll manage, and I'm looking forward to this new algorithm that will be maybe the next leap in science, whatever that is.
I think networking is a very essential piece of this puzzle, because if we look into the human societies, we are able to organize our works in layers. So we create teams, departments, we delegate to politicians, to parliament, and in all those layers we need to synchronize and we need to communicate. When moving it to the AI world, we need networking in order to be able to have a distributed intelligence being shared. So networking, I think, it is a very essential part of AI, especially in the long run, if we are going to build civilizations where AI agents are going to be part of it.
Yeah, I want to mention one thing when Wolfram said that we need to also rethink, for instance, the training algorithm and so on. So what I see these days is that, I mean, research typically looks, I mean, because the research in AI is so much rapidly progressing that people typically look, let's say, for the next big thing, but on a very short time scale. Yeah, so whereas, I mean, for instance, changing an algorithm might take research work of, I don't know, maybe 2-3 years. So I'm just a bit worried that, I mean, research is looking more and more for these low-hanging fruits so that you can keep up with this amazing pace which you see these days, but that people are maybe not that willing anymore to really dig deep and think for a long time about one fundamental problem, for instance, like the training algorithm. So maybe I'm wrong, maybe I see that too pessimistic, but I mean, I think this is something which one need to contemplate.
Yeah, I completely agree. I think if you round to the first digit behind the comma, we have come to a stop. 29,000 papers were submitted to AAAI. I don't know, it must be even more for NeurIPS, right? I mean, honestly, who of you can read 29,000 papers in a month? Because every month this many papers, right? And then there's all these things coming out on archive. We've lost control. Right? I mean, our brain has become the bottleneck which is slowing everything down. We don't know how many of these 29,000 papers at AAAI are identical. There must be some that are very close to each other. So I mean, how is this going to go? It's 20, 30 years ago, I read a paper in cellular biology. And some cellular biologist was saying, we've published close to 1 million papers on the chemistry of the cell. We have nobody in the whole community who thinks about whether we're done, whether all of these papers in sum give us all that there is to know about the cell. And this was 20 years ago. You know, another 1 million papers have appeared. And we have simply no way of telling when we're done. The cellular biologists are continuing to publish because that's their job, right? They want to get tenure and so on. But we have come to, I don't know what the state is, but it's not good.
I fully agree with Oliver and Gita. I think we came at a stage, in art they call it kitsch. So kitsch is where you try to replicate art in a quick, by copying patterns, but without really have genuinity in it. And our papers look more and more like kitsch papers and less pure act of genius. And I think that is a major problem. I fully agree.
Yeah. So the next question is also relevant to these discussions, as we have mentioned ethics in some of the talks in the workshop. We also have mentioned ethics as part of the discussions. So how should we address the ethical implications of embodied AI, so especially in domain like healthcare, care, and even defense? Yeah.
I mean, Ben pointed at this yesterday, and I really liked his presentation. And we had also, like, Gita's talk also was related to this, because like, the problem right now is that we also don't know what these systems actually do, and we are unable to make predictions. And maybe this is something that we also should investigate more. But if you look at self-driving cars, like Waymo is driving in several cities in the US without drivers, right? But they have tested it like extensively, and this has cost, I do not know how much, but billions of dollars. And we cannot afford this, right? We cannot have like every company that builds a humanoid robot for homes that doing exactly this. This simply doesn't scale. It's also probably like something that we need to have better architectures and better methods to basically be sure that the system like does only this what it is supposed to do and nothing else. And this is a key problem right now as well. Although I like this the time, right? Exploring stuff, how far can we get, right? And having this wow factor, right? That, look at this, look at the transformer, what it can do with ChatGPT. But in the end, we need to have different approaches to deal with these systems and basically having that what is called trustworthiness and all these topics or all these terms behind this.
Yeah, I mean, I completely agree. Yeah, so I said it in the talk. I think that is a direction which is extremely important because it will then also, let's say, save us maybe a lot of simulations, because if this is already embedded in the system, let's say reliable by design, I mean, it will save us energy, it will save us a lot of money. And also, I mean, since you mentioned ethics, there are also some directions. For instance, at LMU, we have this Munich Center for Mathematical Philosophy who actually aim to embed ethical considerations in formulas in logic, which could then also be built into the system. And I think it would be important maybe to strengthen those directions more, but also link them to, let's say, people, for instance, in robotics, or in general to manufacturers who then could already design that, so ethical by design in a certain sense.
Okay. I don't have. Okay, great. It's almost 1 hour already. Yeah, so we started with the challenges for embodied AI. So let's conclude with a final question on the opportunities. So in your view, so what do you see the biggest opportunities for breakthroughs in embodied AI in the coming 5 years? Biggest opportunities.
My 5 years is a really short time frame, but my hope is that we will see some cool applications, in particular a robotics application with these systems. And I would be very happy if there is at least one that we can see where we have these robots in the real world and doing something that they were not able to do before. But finding this business case is extremely difficult, but I'm optimistic that someone will find it and we will see something in the near future.
Yeah, I mean, I also think there are great opportunities. Let me just pick one and maybe a wish to people in robotics. So I would wish that maybe within 5 years I can buy a robot, I can put it in my house, and when I return in the evening, everything is done in my house, the house is cleaned, the dishes are done, and so this would be something like, I think for everyone, a great application.
I fully agree. I think that in the next 2 decades, this will be the decades of intelligent robots. We have built some foundations in terms of agents that are able to think in the virtual world, the large language models. They are moved to acting with agentic AI. And now it's time to get the genie out of the bottle and put it into the real world. And then we can make all the wishes we want to the genie in terms of all sorts of household and real world applications. So I think that in the next 2 decades are the decades of robotics and AI.
So it's what I think is going to happen, what I hope is going to happen. Both. Okay, what I hope is easy. I hope that more people actually buy robots for their research lab with complex end effectors and use them to realize that many of the intuitions we have about robotics as a problem are wrong. Right? So I think basically more people need to understand robotics to a deeper level. And then we wouldn't have many of the things that we see today. So I hope that this will happen. And this is 5 years. And I also hope that as a consequence, or maybe in parallel to that, people, once they start questioning their intuitions and their assumptions, will discover new ideas. And it's not about a competition, well, maybe a little bit, but it's more that we need several ideas to cross-pollinate. If we have a monoculture, I don't think it's a healthy state for any discipline that is facing a big unsolved problem. So I hope within 5 years we'll have several competing views on what the right thing to do is. in embodied AI.
Yeah, totally agree. And also, I have my own hope as well over the next 5 years. I hope the public can be more patient for embodied AI as we are deploying intelligence in the real world. And when we deploy such robots in factories and our daily life, so they may make mistakes. So the public could be more patient if they make mistakes, and then we can improve the hardware, the software, so that we can get better embodied AI. Yeah. Thank you all for the great discussions and sharing your insights into embodied intelligence. And we look forward to the deployment and development in the next few years. Okay, let's thank the panel for their insightful comments.
So, panelists, please don't go away. I want to have all the speakers here on stage. All the speakers who are here, we are going to take a picture, and then there will be a gift for all the speakers. Thanks all for coming. This ends the scientific part of this workshop. I don't want to leave. We have this networking lunch right now afterwards, but I don't want to leave without also giving a big thank you for all the people who helped us, in particular Jade, who did a ton of work. And if you found this was a smooth workshop, this is basically her contribution. And I think it's worth a big applause. Involved was also Susanne. She isn't here today because she spends her vacations at the Côte d'Azur, but maybe we can give a clap to her and thank you to her as well. And finally, I want to thank our sponsors sitting there in the corner, the Huawei people, for forcing me to organize this workshop, and also organizing this in this beautiful place here in Nuremberg. And thank you all for coming. I hope you enjoyed it. Enjoy Nuremberg, and thanks Huawei for the great support.